Hello, and welcome to the second course in the Software Design and Architecture specialization, brought to you in partnership by the University of Alberta and Coursera. In this course, we'll be exploring design patterns. If you're joining us for the first time, you may want to consider visiting our first course in the specialization on object-oriented design. Although if you're just interested in learning about design patterns, all of our courses stand alone as individual courses. This course is just like the others in our specialization. It consists of 4 modules, with the first 3 focusing on the content. You'll complete assignments for the capstone project throughout the course, but the rest of the work will take place in the 4th module. So what are we going to cover in these modules? What's next in your journey to designing it right? What is a design pattern? Well, design problems and applications can be resolved through design patterns commonly applied by experts. In this course, you will extend your knowledge of object-oriented analysis and design by learning how to apply design patterns to addressing these design issues. Through a survey of established design patterns, you will gain a foundation for more complex software applications. You also see several design principles to make your software more reusable, flexible, and maintainable. Finally, we'll teach you how to identify bad software designs by referencing a catalog of code smells. When you reach the capstone assignments in this course, you will get to apply your newly acquired knowledge. You'll be challenged to critique an existing Java application for code smells. You'll also get the opportunity to redesigning an application to apply design patterns. For the first module, we'll be teaching you about creational and structural design patterns. So let's begin.
In software engineering, you will often come across the same design problem many times. There are so many ways to deal with these recurring problems, but over time some solutions are preferred over others because they're more flexible or reusable. A design pattern is a practical, proven solution to a recurring design problem. Instead of solving a particular software problem by basic object-oriented programming principles every time, where you would have to decide what objects to use, how objects need to relate, and so on, you can use previously outlined solutions that expert developers have often used. These design solutions are not theoretical proposals of only academic interest. These are actual solutions that are used in industrial software. Think of design patterns like the way you would think of recipes in cooking. There are some dishes that people have experimented with and cooked over and over again. After a while, a certain way of cooking a particular dish would be preferred because it creates the best tasting dish. Over the years, developers have experimented with many different design solutions, and these design patterns outline solutions that often create the best outcome. There are 23 design patterns identified in a famous book called Design Patterns: Elements of Reusable Object-Oriented Software by authors Gamma, Helm, Johnson, and Vlasides. This course will go through a selection of these patterns. However, it's important to note that it won't be so simple to look at a software design problem and automatically know which design pattern to use. There are many design patterns available, and sometimes one particular design pattern may seem applicable, but it may not actually be the right fit to the problem at hand. Using design patterns is sort of like playing a game of chess. There are many ways to win by putting your opponent in checkmate. A beginner chess player may only know the basic moves of each piece, whereas an expert chess player will look for appropriate patterns on the board. There are established chess patterns called the exposed king or the isolated pawn, for example, and these are patterns that experts will look to exploit while playing the game. Through experience, they are better able to judge which patterns to use or create in a particular situation to win the game. Similar to chess, beginner software developers might only know the elements of language syntax in programming software. They know elements like how to create a for loop, a method, and so on. But with more practice and experience, these software developers will write more idiomatic code that follows common conventions. Also, they can become design experts who know the design patterns to use in solving particular software design problems. Another thing to note about design patterns is that it's not just a concrete set of source code that you memorize and put into your software, like Java libraries or frameworks. Design patterns are a bit more conceptual. It is knowledge that you can apply within your software design to guide its structure and make it more flexible and reusable. So why should you use design patterns? Design patterns help software developers so that, instead of building everything from scratch, they have a guide that helps them to solve design problems in the way experts do. A beginner athlete may have the natural talent and basic knowledge of the sport they're playing, but a coach with years of experience will be able to help that athlete become better and use their talent to achieve greater things. Design patterns are already proven by experts, and they've gone through the hardships. You can skip the trials they've already gone through and just go straight to creating better written software. Finally, design patterns help to create a design vocabulary. Rather than having to explain the details of a design solution over and over again, you can simplify the discussion by having a suggestive word to describe it. For example, there is a very common design problem in software where you have two objects, and the first object depends on the second object. If the second object changes, the first object should be notified. This is a situation that occurs often in software, and it would take some time during a discussion to describe a solution involving superclasses or interfaces and certain methods. Design patterns help to address this issue by giving each pattern a name and making it easier for developers to communicate. Instead, you can simply say, we'll use an observer design pattern here. Prior knowledge of this particular pattern outlines the solution and clarifies the original situation, so that a discussion can focus on other issues. Knowledge of design patterns leaves less room for misunderstanding. My description of the situation and solution could have been vague, and you could have misunderstood the design to be implemented. If I simply say, this is an observer pattern, we both know exactly what we're discussing. You will learn many design patterns throughout this course. You will learn what to look for and how to use each design pattern. Design patterns are important techniques to use and learn as you design software. So now it's time to start designing like an expert. There are many design patterns you can find in books and via the internet. One of the most famous books on the topic is Design Patterns: Elements of Reusable Object-Oriented Software. This book was written by 4 authors who were given the nickname the Gang of Four. The Gang of Four's book pulled from their experience as developers. Each author had written their own programs and graphical applications, and while doing so, found patterns emerging in their design solutions. As a group, they decided to formalize the patterns into a useful reference. The patterns are organized to be readable, and they are often named to suggest their purpose. With these patterns, they formed a catalog. In this lesson, I will go over the Gang of Four's design pattern catalog. This catalog is not like a recipe book. You can't pull universal patterns out of it to use in your code like puzzle pieces. Instead, it's closer to a list of tropes. A trope is a storytelling device or convention often found in fiction. Films and TV shows use a pattern of storytelling. For example, you might see the hero's journey recur in fiction. The hero's journey is a pattern of storytelling that follows a very distinct order. The hero starts from humble beginnings in an ordinary world, finds a special world, and must face trials in order to return home. This trope can be found in hundreds of pieces of fiction. Just like tropes recurring in film, design patterns emerge in software. Occurrences of the same pattern can be found in thousands of programs. A very simple example of a pattern would be defining and calling methods. The Gang of Four's catalog contains a number of patterns and solutions with a variety of different purposes. A collection of patterns that are related to a certain problem space is called a pattern language. Depending on the context of the problem, you would need to use different pattern languages. When designing games, you might use a different pattern language than if you were creating accounting software. For games, you have design words such as encounters, quests, and players. These words are important in design patterns for game software, but would not be found in design patterns for accounting software. In accounting software, double-entry bookkeeping is a vital design solution to reduce errors and ensure consistency in the transactions. Double-entry bookkeeping would not need to be defined in a pattern language for game design. Think of it like human languages. If you were trying to speak with someone who only spoke Mandarin, you would choose the appropriate language to converse with them. Just like you would choose the language of speaking based on your audience, you would also choose your pattern language and design patterns based on the problem space. Now it's your turn to define a pattern language. There are 23 patterns found in the Gang of Four's catalog. I will go over the categories of patterns that the Gang of Four defined. One of the main categories of patterns involves creational patterns. Creational patterns tackle how you handle creating new objects. There are several different patterns based upon creating and cloning objects. For example, if you are creating an object that is similar to an existing one, instead of instantiating a new object, you might clone existing objects. You might make the choice to clone rather than instantiate based upon the language you are implementing in. Languages without the notion of classes would encourage you to clone and add to existing objects. A language like JavaScript does not contain traditional classes to be instantiated. Objects are instead cloned and expanded to meet the purposes of those particular instances, called prototypes. JavaScript allows for changes to these prototypes at runtime. Languages like Java and C#, on the other hand, rely heavily on instantiating objects using specific classes defined at compile time. The differing ways of creating objects can strongly impact how you solve a problem. An implementation language is how a design pattern language is realized, which can heavily influence what patterns are possible to use. Another pattern category used by the Gang of Four involves structural patterns. Structural patterns describe how objects are connected to each other. Previously, we examined major design principles like decomposition and generalization, and how they are expressed in UML class diagrams with association, aggregation, composition, inheritance, and interface relationships. There are many different ways you can structure objects depending on the relationship you'd like between them. Not only do structural patterns describe how different objects have relationships, but also how subclasses and classes interact through inheritance. Structural patterns use these relationships and describe how they should work to achieve a particular design goal. Think of a structural pattern like a food dish, with a combination of flavor pairings. A flavor pairing determines which ingredients may be combined together to form a suitable relationship. Some ingredients are mixed together to the point where they are nearly indistinguishable, such as garlic and chickpeas in hummus. Others are combined, but still maintain some independence, such as a salad of mixed vegetables. Some food just pairs well with others and is not physically combined, such as wine and cheese. The relationships among the food are defined by the pairings. Similarly, in software, each structural pattern determines the various suitable relationships among the objects. The final pattern category involves behavioral patterns. These patterns focus on how objects distribute work. They describe how each object does a single cohesive function. Behavioral patterns also focus on how independent objects work towards a common goal. Think of a behavioral pattern like a race car pit crew at a track. In the pit crew, the roles of the members describe how the team is able to achieve victory, which is their common goal. Each member has a specific responsibility, their role in the race. Some members change the tires, others unmount and mount the wheel nuts, others refuel the car, but all must work together to win. Like a game plan, a behavioral pattern lays out the overall goal and the purpose for each of the objects. All of these categories may not be so clear-cut. Some patterns have elements that could make them span categories. The Gang of Four just uses these categories in order to organize and characterize the patterns in their book. Patterns will help you as a designer to develop an intuition for and appreciate object-oriented design. By looking for specific design patterns, you can better recognize object-oriented design elsewhere. Patterns sometimes come with their share of consequences. You must decide which ones will suit your problem or design issue the best. There are trade-offs that must be made when designing your systems. Some patterns may be more resource-intensive, like more memory or processing. By learning different design patterns, you will be able to design software for different purposes and in different ways. Singleton is a creational pattern, which describes a way to create an object. The singleton pattern is one of the simplest examples of a design pattern. However, you will see that it is a powerful technique. As its name suggests, the singleton design pattern is about something singular, having only one. But what is it referring to? What do we only want one of? The singleton pattern refers to having only one object of a class. Let's say that you're working on a mobile app where the user can play poker. This game has a preferences class to define where all the settings for the user are stored. These preferences include visual elements, such as the color of the playing surface and the design on the backs of the cards. Imagine if more than one instance of the preferences class existed. When the user is setting their preferences, which preferences object is saving those choices? And when the game is being displayed, which preferences object is used to determine the design and colors for the game? As you can see, having another preferences object doesn't make much sense and could lead to conflicts or inconsistencies. Another goal of the singleton design pattern is that the single object is globally accessible within the program. Now that we've discussed the design goal of having only one instance of a class, how is this actually implemented? If you're working on a small project on your own, you may do this informally. After instantiating a class, you make a mental note to yourself not to create another instance, and the problem is solved. Sort of. If you forget and create another instance, then you might cause headaches for yourself. This is also definitely not a workable solution in larger projects, or projects with multiple developers. We would like to prevent errors arising from multiple objects of a singleton class being instantiated. The solution is to build this one and only one goal into the class itself, so that creating another instance of a singleton class is not only frowned upon, but impossible. In this way, you codify your design intent within the software. How do you do this? If you have a class with a public constructor, this constructor may instantiate an object of this class at any time. There is nothing to prevent a different part of the software creating another object of this class. Instead, then, you give the class a private constructor so that the constructor cannot be called from outside the class. This creates an apparent contradiction. The constructor is private, so it cannot be called outside its class. So how do you create an object of this class without a public constructor? There are two key components to get around this. The first is to declare a class variable, called, say, unique instance. This class variable will refer to the one instance of your singleton class. You declare the variable as private, so that it can only be modified within the class. The next step is to create a public method in the class that will create an instance of this class, but only if an instance does not exist already. We can call this method getInstance. This method will first check if the unique instance variable is null. If it is null, then it will instantiate the class and set this variable to reference the object. If the unique instance class variable currently references an object, in other words, if there is already an object of this class, then the method will simply return that object. Because the getInstance method is public, it can be called globally and used to create one instance of the class. In a sense, it replaces the normal constructor. Our class now realizes the singleton design pattern because there can only be one instance, which is globally accessible. By hiding the regular constructor and forcing other classes to instead call the public getInstance method, we added basic gatekeeping to ensure that only one object of this class is ever created. The very same method is used to globally reference the single object if it has already been created. Now we can use our singleton class in a large project and not worry about multiple instances confusing developers and creating conflicts. Another advantage of this version of a singleton class is that the object is not created until it is truly needed. This is called lazy creation. Lazy creation could be helpful if the object is large. It is not created until the getInstance method is called, which is more efficient. Of course, there can be trade-offs to using the singleton design pattern. If there are multiple computing threads running, there could be issues caused by the threads trying to access the shared single object. To decide if singleton, or any other design pattern, is the best design for the job, it helps to have a good idea of how it works and its potential consequences. Design patterns are defined by their purpose or intent, and not the exact code, so you may see variations of how singleton is realized, but their goal is always the same: to provide global access to a class that is restricted to one instance. In general, this is achieved by having a private constructor with a public method that instantiates the class if it is not already instantiated. There are many objects that we would like only one of: the preferences of an app, the print queue of your printer, the software driver for a device. It could be confusing or even disastrous to have multiples in these cases. The singleton pattern restricts a class to one object by building this intent into the code. It can be a powerful technique on its own, or in combination with other design patterns. As you design, think of where you can use the singleton pattern to ensure for yourself, or other developers on the same project, that a given class has only one object. Now, we're going to talk about another creational pattern, the factory method pattern. Along the way, we will also learn about a factory object. Just like a factory in the real world, the purpose of these factories in object-oriented programming is to create objects. Using factories makes your software easier to maintain and change, because object creation happens in the factories. The methods that use these factories can focus on other behavior. Imagine that your software implements an online store, and that you want to create objects to sell in that store. Let's use a knife store, for example. There are many different types of knives, but let's start with steak knives and chef's knives. You have a superclass, knife, with subclasses steak knife and chef's knife. You write a method to order a knife, which will first create one of these knife objects and then prepare it for shipment. Let's say that the preparations that it performs on the knife are sharpen, polish, and package. Your method looks like this. The method first declares a knife variable, which will refer to the knife object to be created. The conditionals determine which subclass of knife is actually instantiated. The act of actually instantiating a class to create an object of a specific type is called concrete instantiation. In Java, you usually do concrete instantiation with the new operator. You will soon see that concrete instantiation will be the primary purpose for our factories. The next step is to call some methods that are common to the different types of knife objects: sharpen, polish, and package. These methods do not care what type of knife is created. All they want is a knife to operate on. Imagine that your store adds more and more knife types as its sales improve. New subclasses are added as needed: bread knife, paring knife, etc. In this example, the list of conditionals grows and grows as new knife types are added. Notice that what we do with the knife after creating it doesn't change. All of these knives need to be sharpened, polished, and packaged. This is all getting pretty complicated. What if instead of making your knives in the store, you could make them somewhere else? Just as in the real world, objects are usually made in factories. We can create a factory object whose role is to create product objects of particular types. So the sharpening, polishing, and packaging will stay where it is in the order knife method, but you will delegate the responsibility of product object creation to another object, a knife factory. You're going to move the code for deciding which type of knife to create, and the code for deciding which subclass of knife to instantiate, into the class for this factory. The class for a knife factory is shown here, with a createKnife method. Some other code will instantiate a knife factory object, but once done, you can use the createKnife method to make knife objects of particular types. This is almost the exact same code used to create a knife object in the previous example. It has just been moved into a method of a new class called a knife factory. In general, a factory object is an instance of such a class, which has a method to create product objects. Now, this knife factory can be used by the knife store class. In other words, the knife store is now a client of the knife factory. Look at this example. In this example, the knife factory object to use is passed into the constructor for the knife store class. The order knife method is very similar to before. However, instead of performing concrete instantiation itself, it delegates this task to the factory object. What have you gained? First of all, the knife store and its order knife method may not be the only client of your knife factory. Other clients may use knife factories to create knives for other purposes. Maybe there's a method for bulk orders or quality testing. Since all of the actual knife creation happens in the knife factory, you can simply add new knife types to your knife factory without modifying the client code. If there are multiple clients that want to instantiate the same set of classes, then by using a factory object, you have cut out redundant code and made the software easier to modify. Instead of hunting down multiple snippets of similar instantiation code, you can simply add or remove the particular subclasses to instantiate in your factory. If you change the way that subclasses are instantiated, you only need to change your factory, rather than every client. Look at the order knife method. As far as it's concerned, as long as it receives a knife object from the factory, it can satisfy its responsibilities. This allows the developer to make changes to the concrete instantiation without touching the client method. The client method does not need to name concrete knife classes and now deals with a knife generalization. This is called coding to an interface, not an implementation. Think of this like a real-life factory. Usually, when a store is selling something, like the knife in our example, the store itself does not make that item. Instead, the store gets their knives from a knife factory. This knife factory makes knives for the store, but may also have other clients, such as other stores that need knives. If the factory changes the way it makes knives, then the stores don't care, as long as they receive knives of the right type. Perhaps the blade material changes or the handles change shape. These changes are made in the factory, not in the store. Okay, so we can use a factory object to instantiate product objects. Although it is a useful technique, the factory object is not actually one of the Gang of Four design patterns. Let's take a look at the factory method pattern. The factory method pattern approaches the creation of specific types of objects in a different way. Instead of using a separate object, a factory object, to create the objects, the factory method uses a separate method in the same class to create the objects. You're going to see that the power of the factory method comes from the way it creates specific knife products. To create specialized product objects, a factory object approach would subclass the factory class. For example, a subclass of our knife factory called Budget Knife Factory could create Budget Chef's Knife and Budget Steak Knife product objects. A Quality Knife Factory could create Quality Chef's Knife product objects or Quality Steak Knife product objects. A factory method approach instead has a Budget Knife Store subclass of Knife Store. The Budget Knife Store has a method, the factory method, that is responsible for creating Budget Chef's Knife and Budget Steak Knife product objects instead. The factory method design intent is to define an interface for creating objects, but let the subclasses decide which class to instantiate. What does this look like? Let's look at the Knife Store superclass first. First of all, Knife Store is now abstract. This means we cannot instantiate a Knife Store. Instead, you will need to have Knife Store subclasses, such as Budget Knife Store or Quality Knife Store. These subclasses will inherit the same order knife method. Just like before, the order knife method uses a factory, but now it is a factory method. The factory method in this example is createKnife. It is declared in the superclass, but it's abstract and empty. We left the factory method empty and called it abstract because we want the factory method to be defined by the subclasses. Whenever a knife store subclass is defined, it must define this createKnife method. Let's take a look at what a knife store subclass looks like. Now you would instantiate a budget knife store. The budget knife store has its own method for creating knife objects. A different knife store, such as quality knife store, would have a different factory method. You can't define a new knife store subclass without providing this method. Because the budget knife store is a subclass of knife store, it inherits the order knife method. You run the common order knife method from any subclass of knife store. All the subclasses of knife store, budget knife store, quality knife store, maybe family knife store, inherit the order knife method. However, each subclass must define its own createKnife method. Let's take a look at the UML class diagram for one knife store. The UML class diagram gives you some important information. First of all, both knife and knife store are italicized to denote abstract classes. You cannot instantiate these classes directly. You must define subclasses of them. The UML diagram shows only one subclass of knife, but there could be more. Budget chef's knife, budget paring knife, etc. We could also have more than one knife store, maybe quality knife store or family knife store, which would make other types of knives. The createKnife method is also abstract in knife store. This means that any subclass of knife store must define this method. So, budget knife store and any other knife store subclass we define must have its own createKnife method. This is the core of the factory method design pattern. The factory method pattern always follows the same general structure. Let's check out the UML class diagram. We have an abstract creator class. This class contains methods that only operate on generalizations. In other words, as long as we give these methods the products they want to operate on, they're happy. In our example, the product was knife. The creator also declares the factory method abstractly, so that each concrete creator class is obliged to provide a factory method. The concrete creator is a subclass of the abstract creator. We call it a concrete creator because it is responsible for concrete instantiation, the actual act of creating objects. The concrete creator also inherits methods from the abstract creator. Factory method is a method in our concrete creator subclass. Every time the developer adds a concrete creator subclass to the design, they must define a factory method to make the right products. This is how the subclass decides how to create objects. The product superclass, which was knife in our example, generalizes the concrete products. As far as the creator class is concerned, its methods only operate on the general product, never the concrete products. The concrete products are made by the concrete creator. The type of product made is decided by which concrete creator is made. In our example, the budget knife store made budget chef's knife and budget steak knife, while the quality knife store could make quality chef's knife or quality steak knife. In this lesson, we covered the factory method design pattern and factory object. A factory is generally a method or object that allows you to create other objects. Remember that the act of object creation, usually with the new keyword in Java, is called concrete instantiation. Factories allow client code to operate on generalizations. This is called coding to an interface, not an implementation. As long as the client code receives the object it expects, a knife in our example, it can satisfy its responsibilities without worrying about the details of object creation. A factory object may be a useful tool. It is an object that creates other objects. It could be useful if many parts of the software want to create the same objects. You can even create specialized factories by having subclasses of the factory class. The factory method pattern is a little bit different. Instead of using another object to create objects, we separate out object creation into another method, a factory method. Now, instead of working with the factory object, we specialize or subclass the class that uses the factory method. Each subclass must define its own factory method. We say that we are letting the subclasses decide how objects are made. By separating the actual object creation from other behavior using factories, the code becomes cleaner to read and easier to maintain or change. The client code is simplified, and the details of object creation are moved into the factories. The code becomes more extensible and harnesses the power of object-oriented design principles, such as inheritance, to allow you to specialize your object creation. As parts of your system become larger, they naturally become more complex. This can be potentially confusing for the client classes in your system to use. System complexity is not always a sign of poor design, though. The scope of the problem you're trying to solve may be so large it requires a complex solution. Client classes, however, would prefer a simpler interaction. The facade design pattern provides a single, simplified interface for client classes to interact with the subsystem. What is a facade? If you've ever gone shopping at a retail store, eaten at a restaurant, or ordered anything online, you've had experience interacting with a real-world facade design pattern. Picture yourself walking down the street, looking for a place to have dinner. What do you look for when you're at street level? Naturally, you look for a sign on the face of a building that indicates that the contents within the structure can provide you with a dining service. Similarly, when you're shopping online, you look for some outward indication that the website you're on has a virtual storefront. These outward-facing indicators are used to communicate to the public what types of services are available. When a waiter takes and places your order, or when an online sales platform sends your order to be fulfilled, they are acting as part of a facade by hiding away all the extra work that needs to be done. You are able to purchase goods and services without having to know how the request is processed. The entire construction of the buildings, waitstaff, menus, websites, and many other components are behind facades. Keep in mind that a facade does not actually add more functionality. A facade simply acts as a point of entry into your subsystem. In software, the facade design pattern does exactly what a waiter or salesperson would do in real life. A facade is a wrapper class that encapsulates a subsystem in order to hide the subsystem's complexity. This wrapper class will allow a client class to interact with the subsystem through a facade. Let's take a look at how client code would interact with the subsystem without a facade class for a simple banking system. Without a facade class, the customer class would contain instances of the checking, saving, and investment classes. This means that the customer is responsible for properly instantiating each of these constituent classes and knows about all their different attributes and methods. This is like having to manage all of your own financial accounts in real life, which can be complex with lots of accounts, instead of letting a financial institution do it for you. Instead, we introduce the bank service class to act as a facade for the checking, saving, and investment classes. The customer class no longer needs to handle instantiation or deal with any of the other complexities of financial management. Since the 3 different accounts all implement the iAccount interface, the bank service class is effectively wrapping the account interface in classes and presenting a simpler front to them for the customer client class to use. The facade design pattern is simple to apply in our bank accounts example. It combines interface implementation by 1 or more classes, which then gets wrapped by the facade class. Let's see how to do that. Step 1. Design the interface. This Java interface is the one that will be implemented by the different account classes and will not be known to the customer class. Step 2. Implement the interface with 1 or more classes. Remember that interfaces allow us to create subtypes, which means that checking, saving, and investment are subtypes of iAccount and are expected to behave like an account type. Next, you implement your interface with classes that will be wrapped with our facade class. In this example, you are only implementing and hiding 1 interface, but in practice, a facade class can be used to wrap all the interfaces and classes for a subsystem. It is your decision as to what you want to wrap. Step 3. Create the facade class and wrap the classes that implement the interface. The bank service class is the facade. How does it do that? Notice that its public methods are simple to use and show no hint of the underlying interface in implementing classes. Another thing to note is that we set the access modifiers for each account to be private. Since the entire point of the facade design pattern is to hide complexity, we use the information hiding design principle to prevent all client classes from seeing the account objects and how these accounts behave. Step 4. Use the facade class to access the subsystem. Client classes can access the functionalities of the different accounts through the methods of the bank service class. The bank service class will tell the client what type of actions it will allow the client to call upon, and then will delegate that action to the appropriate account objects. Now that we have our facade class in place, our client class can access its accounts through the bank service. Your customer class does not need to worry about creating and managing its own accounts. The customer simply needs to know about the bank service and the set of behaviors the bank service is capable of performing. We've effectively hidden the complexity of account management from the customer using the bank service facade class. The facade design pattern is similar to other design patterns in that it uses encapsulation to hide the details of some part of our system. It can be easy to get these design patterns mixed up, so let's summarize what characterizes the facade design pattern. The facade design pattern is a means to hide the complexity of a subsystem by encapsulating it behind a unifying wrapper called a facade class. removes the need for client classes to manage a subsystem on their own, resulting in less coupling between the subsystem and the client classes, handles instantiation and redirection of tasks to the appropriate class within the subsystem, provides client classes with a simplified interface for the subsystem, acts simply as a point of entry to a subsystem, and does not add more functionality to the subsystem. The facade design pattern is a way to provide client classes with an easier means of interacting with the parts of your system. Complex subsystems can be difficult to use and navigate. By providing a simpler interface through a facade, client classes will have an easier time successfully using your software. I'm sure this looks like a familiar situation. You have a device that expects one sort of connector, but you have something that provides a different connector. Because of the mismatch, you can't make the connection. So, you'll need an adapter to, in effect, turn the different connector into one your device expects. Adapters are frequently used because different vendors will have different and evolving connectors for their devices. For example, a common connector for a peripheral device like a keyboard was once PS2, but computers in the mid-1990s started to only support USB ports. So people who had the older PS2 keyboards needed an adapter to use them with the new computers. This adapter converted a computer's USB port into a connector that the old keyboards could plug into. Software systems also face the same compatibility issue. Instead of having physical connectors, systems will have incompatible software interfaces. That is to say, the output of one system may not conform to the expected input of another system. You'll find that this is a recurring problem when your pre-existing system needs to incorporate third-party libraries or needs to connect to other systems. The adapter design pattern will help facilitate communication between two existing systems by providing a compatible interface. This design pattern is composed of several parts. Let's take a look at what they are. The client class will be part of your system that wants to use a third-party library or external system. The adaptee is, say, a class in the third-party library or external system to be used. The adapter class sits in between the client and the adaptee. It will implement a target interface, which is the interface that the client will use. The adapter conforms to what the client is expecting to see. The client sends a request to the adapter using the target interface. The adapter will then translate the request into a message that the adaptee will understand. Once the translation is finished, it will send the translated request to the adaptee. Now let's take a look at how we can implement the adapter design pattern in a specific example. In this example, we have a pre-existing web client that we want to use to talk to another web service. Our web client expects to send any object in a request, but the service only supports a JSON object. We need to use an adapter to convert our object request into a JSON object. Step 1. Design the target interface. You create the target interface that your adapter class will be implementing for your client class to use. Step 2. Implement the target interface with the adapter class. Your adapter provides the methods that will take the client class's object and convert it into a JSON object. This means that the adapter can convert any instance of a class that the client can create and send that in a request. The adapter class also handles transferring the translated request to the adaptee. The client class only needs to know about the target interface of the adapter. Step 3. Send the request from the client to the adapter using the target interface. The web client is responsible for doing some work to create your message for you. In your main program, you need to instantiate the web adapter, the web service, and the web client. The web client deals with the adapter through the web requester interface to send a request. Notice how your web client doesn't need to know anything about the web service, like its need for JSON objects. The adaptee is hidden from the client by the wrapping adapter class. So if two interfaces are incompatible, why don't we change one, or even both so that they're able to talk to each other? Well, if you've noticed on our example, we don't show the implementation of the web service class. This is because it's meant to represent a third-party library or external system that we may not have direct access to. If we did have direct access to those libraries or systems, an update by the vendors may make our changes inconsequential, or our changes may actually break those libraries or systems. Then why don't we just change our system's interface? Well, that might work, but what if a subsystem is using it? Changing assumptions like this can inadvertently break another part of our system. Remember that an adapter is meant to wrap the adaptee and expose a target interface to the client, indirectly change the adaptee's interface into one that the client is expecting by implementing a target interface, indirectly translate the client's request into one the adaptee is expecting, and reuse an existing adaptee with an incompatible interface. It isn't always practical to rewrite large chunks of your system in order to properly interface with new third-party libraries or external systems. Just because an interface doesn't conform to what your system is expecting doesn't mean that your system has to change. The adapter design pattern is a technique that helps bridge the gap between two incompatible interfaces. This will let you continue to use your existing systems and integrate external sources into them. Buildings are composed of rooms. Although buildings and rooms have slightly different functions, we essentially treat them as generic housing structures. You can enter and exit a building or a room, and they can both be used to store furnishings. So, despite being unique types of objects, they can be dealt with uniformly. The composite design pattern achieves two goals: to compose nested structures of objects, and to deal with the classes for these objects uniformly. The pattern follows this basic design. A component interface serves as a supertype for a set of classes, so that they can all be dealt with uniformly. This is done by enforcing polymorphism. All implementing classes conform to the same interface. An abstract superclass can also be used in place of an interface, as both are allowed for polymorphism, but we'll focus on using an interface here. The composite class is used to aggregate any class that implements the component interface. The composite class will allow you to traverse through and potentially manipulate the component objects that the composite object contains. The leaf class represents a non-composite type. It is not composed of other components. Next, we want to deal with non-composite and composite objects uniformly. By having the leaf class and composite class implement the component interface, we unify them with a single type. The composite and leaf classes are now considered subtypes of component. Depending on the problem, you can have other composite and leaf classes when using the composite design pattern, but only one overall component interface or abstract superclass. Note that a composite object can contain other composite objects, since the composite class is a subtype of component. This is known as recursive composition, which is another name for this design pattern. It can be difficult and confusing to imagine how this design pattern actually looks like because of the apparent cyclical nature of the composite class. The easiest way to visualize it is by thinking of it like a tree. At the root level, we have our main composite object, which is made up of other component objects. At each level, we can add more components below each composite object, like another composite or a leaf. Note that you can only add components to a composite object and not a leaf object. This means that a composite object has the potential to grow the tree, while a leaf object effectively ends the tree where it is. The composite design pattern is used to address two issues. How do we use individual types of objects to build a tree-like structure? And how can we treat the individual types of objects uniformly without checking their types? Now that we know what the UML class diagram of a composite design pattern looks like, and how to interpret it, let's apply it to an example. We will use the earlier example of how buildings are composed of generic housing structures. This structure is considered the component interface. It can be used to describe a building, a floor, or a room, despite each of these being unique types of objects. The housing class is the composite class. A housing is a type of structure which could also contain other structures. This means that a housing object could contain other housing objects. For example, a building could be represented by a housing object, and the building could contain floors. Each floor could be represented by another housing object. We can traverse through the building from floor to floor because the building is composed of floors, all of which are housing objects. A room is considered a leaf class, since a room cannot contain another room. It is contained within a housing, like the floor of a building. We now have a UML class diagram that expresses how to model buildings being made up of housing and room types of structures. Next, let's realize the composite design pattern for the building example in Java. Step 1. Design the interface that defines the overall type. We start off by defining the interface that the composite and leaf classes will implement. This supports polymorphism for your component and leaf classes. Step 2. Implement the composite class. You implement the interface in the composite class. This will give the housing class its own behavior when client code uses it. Since a housing object can be composed of other structures, you will need to represent this containment with a suitable collection. You will also need a method for adding more components to your composite object. Here, we have used a private array list and changed it only through the public addStructure method. To traverse through the components of a composite object, you must be able to retrieve the components when asked. You can also include additional methods which will help with the management of component objects. It is up to you to decide what else to include in your composite class. Step 3. Implement the leaf class. Since the leaf class doesn't contain any components, we don't need to add a collection of components to it or any methods to manage a component collection. We simply need to implement the methods of the iStructure interface. Now that we've finished implementing our building using the composite design pattern, how do we actually use it? We simply construct our building structure by structure. In this example, our building has one floor, which contains a common room and 2 washrooms. This is obviously very simplistic, but it gives you an idea how powerful this design pattern can be. Composite objects can be built quickly and easily. Each component can be expected to have the same set of behaviors without needing to do any type checking. To summarize, the composite design pattern is used to solve the issues of how to build a tree-like structure of objects, and how to treat the individual types of those objects uniformly. This is achieved by enforcing polymorphism across each class through implementing an interface, or inheriting from a superclass, and using a technique called recursive composition, which allows objects to be composed of other objects that are of a common type. You can think of this design pattern as applying the decomposition and generalization object-oriented design principles together to break a whole into parts, but having the whole and parts both conform to a common type. The composite design pattern lets you build complex structures by constructing them using composite objects and leaf objects, which belong to a unified component type. This makes it easier to understand and manipulate the structure, and will lead to more readable, reusable, and meaningful code. There are times in life when it's easier, safer, or more convenient to use a placeholder to represent something or someone else. Individual representatives may be sent to speak on behalf of a company at a conference. Crash test dummies are used instead of real human beings for vehicle collision testing, and a credit card is an acceptable form of payment in place of cash. In each of these situations, an object is represented by a proxy object. The proxy acts as a simplified or lightweight version of the original object. A proxy object is still able to accomplish the same tasks, but may delegate requests to the original object to achieve them. We encounter similar issues in software systems where it is better to use a proxy object in place of the original. This is the goal of the proxy design pattern, which allows a proxy class to represent a real subject class. In this design pattern, the proxy class wraps the real subject class, that is, hides a reference to an instance of the real subject class. The real subject class is a part of your system that, for example, may contain sensitive information, or would be resource-intensive to instantiate. Since the proxy class acts as a wrapper, client classes will interact with it instead of the real subject class. Why do we want to use a proxy class? The 3 most common scenarios for them are 1. To act as a virtual proxy, where the proxy class is used in place of a real subject class that is resource-intensive to instantiate. This is commonly used on images in web pages or graphics editors, because a single high-definition image can be extremely large. If you were to load all of these images at once, it could put a strain on your system's resources. 2. To act as a protection proxy in order to control access to the real subject class. A protection proxy can be used in a learning management system that checks the credentials of a user, so that different users, like students and instructors, can only access the appropriate functions permitted by their role. And 3. To act as a remote proxy, where the proxy class is local and the real subject class exists remotely. Think of this like working on a Google document, where your web browser has all the objects it needs locally, which also exist on a Google server somewhere else. Let's take a look at the general classes and structure of the proxy design pattern. The proxy class wraps, and may delegate or redirect calls upon it, to the real subject class. However, not all calls get delegated because the proxy class is supposed to act as a lighter version of the real subject class, and can do some of its lighter responsibilities. The proxy class will only redirect more substantive requests to the real subject class. But what calls need to be supported in the proxy class? Since the proxy class is meant to stand in for the real subject class, it must offer the same methods. You can ensure that by having both these classes implement a common subject interface, which also allows for polymorphism. Since the proxy and real subject classes are both subtypes of subject, a client class can interact with the proxy, which will have the same expected interface as the real subject. Let's take a look at a practical application of the proxy pattern. Suppose you run an online retail store with global distribution and warehousing. How would you know which warehouse to route orders to fulfill customer orders? You may run into an issue where you route orders to a warehouse that doesn't have stock for an item in a customer order. You need some way to determine which warehouse to send the orders to. A system that routes the orders for fulfillment to an appropriate warehouse will prevent your warehouses from receiving orders they cannot fill. So, how would you implement this system? You can use the proxy design pattern to have a proxy protect your real subject, the warehouses, from receiving orders if the warehouses don't have enough stock to fulfill an order. The iOrder interface defines how you would fulfill the orders. The proxy class and the real subject class will implement the interface differently. This interface declares how to interact with your order fulfillment system. The order fulfillment class acts as the proxy for all your warehouses. It has a list of warehouses that it can delegate parts of customer orders to depending on whether or not a warehouse is capable of fulfilling a part of the order. The warehouse class is your real subject class and will be responsible for actually processing and fulfilling parts of customer orders. The warehouse class will report its inventory to the proxy that asks for it. As shown in the general design overview for the proxy design pattern, the client will interact with your system by using the interface. Now that you've completed the design for your order fulfillment system, the next step is to implement it. Step 1. Design the subject interface. Create the interface that client software will use to interact with your system. This interface will be implemented by the order fulfillment and warehouse classes. Step 2. Implement the real subject class. The warehouse class knows how to process an order for fulfillment, and it knows how to report the current stock of items. Notice that it doesn't need to check if it has enough stock to fulfill an order, because an order should only be sent to a warehouse if it can be fulfilled. Step 3. Implement the proxy class. The order fulfillment class does all the work of checking the warehouse inventory and ensuring that an order can be successfully completed before sending the request to the warehouse. It will ask each warehouse about whether it has enough stock of a particular item. If the warehouse has enough inventory, the item gets added to a new order object that will be sent to the warehouse. The proxy class ensures that an order can be fulfilled before sending the request to your warehouses. This protects your warehouse system from receiving orders it cannot fulfill. The order fulfillment class also lets you separate order validation from the order fulfillment by separating them into two pieces. This will improve the overall rate of processing an order because the warehouse doesn't have to worry about the validation process. Each individual warehouse also doesn't need to worry about how to reroute an order if the warehouse can't fulfill the order. The order fulfillment class can be improved with other functionalities, such as prioritizing sending orders to warehouses based on proximity to the customer, to ensure that orders arrive as fast as possible. The proxy design pattern is useful when you need to defer creating resource-intensive objects until needed, control access to specific objects, or when you need something to act as a local representation of a remote system. To summarize, the main features of the proxy design pattern are to use the proxy class to wrap the real subject class, to have a polymorphic design so that the client class can expect the same interface for the proxy and real subject classes, to use a lightweight proxy in place of a resource-intensive object until it is actually needed, to implement some form of intelligent verification of requests from client code in order to determine if, how, and to whom the request should be forwarded to, and to present a local representation of a system that is not in the same physical or virtual space. The proxy design pattern provides your system with a powerful means of indirection. Proxy classes are robust and can let you build systems that are more secure and less resource-intensive. Coffee is one of my favorite things in the world. I like a simple cup of black coffee, but sometimes I like to switch it up. Are you someone who likes a plain cup of black coffee? Or are you one of those people that likes the more dressed up versions of coffee? Adding more ingredients like milk, flavored cream, or hot chocolate are ways of changing a cup of coffee. We may still think of it as being a coffee-based beverage, but there are expected differences between black coffee and more fancy versions of coffee like a latte or espresso. Regardless of what type of coffee we're drinking, the effects of each ingredient used don't change. For example, coffee will always act like a stimulant because of its caffeine content. This doesn't change if we add milk, change the brewing style, or if it's served at different temperatures. Coffee will still be a stimulant. This holds true for anything that you add to coffee. Someone who's lactose intolerant would still be unable to consume dairy products, even if they were mixed in with coffee. The lactose in milk doesn't change because it's mixed with something else. Even though every ingredient continues to hold its own characteristics, combining them creates a new beverage that may be more enjoyable than when consumed separately. In software, like devising a new beverage, it's beneficial to have flexible combinations of overall behaviors. But we encounter an issue trying to do this dynamically at runtime. That's because the behavior of an object is defined by its class. But the notion of a class and relationships like inheritance are static, that is, happen at compile time. This means that we cannot make changes to classes while our program is running. We'd need to create a new class in order to achieve a new combination of behaviors. As a result, having lots of new combinations would lead to lots of classes, and we don't want that. Given that an object has a certain behavior, can we still, in effect, dynamically attach additional behaviors or responsibilities to it? Luckily, there is a decorator design pattern to achieve this. It uses aggregation to combine behaviors at runtime. Aggregation is used to represent a has-a, or weak containment relationship between two objects. We can use the has-a relationship to build a stack of objects, where each level of the stack contains an object that knows about its own behavior and augments the one underneath it in the stack. This is what an aggregation stack looks like. Object A is a base object because it doesn't contain another object. It will have its own set of behaviors. Object B aggregates Object A, allowing Object B to, in effect, augment the behaviors of Object A. We can continue to add objects to the stack in such a way that Object C aggregates Object B to, in effect, augment the behaviors of Object B. The aggregation relationship is always one-to-one in the decorator design pattern in order to build up the stack so that one object is on top of another. To achieve an overall combination of behavior for the stacked objects, you would call upon the top element, which is Object C. Object C would call upon Object B, and Object B would call upon Object A. Object A responds with its behavior, then Object B adds its increment of behavior, and then Object C adds its increment of behavior. The actual structure of this design pattern makes use of both interfaces and inheritance, so that the classes conform to a common type, whose instances can be stacked up in a compatible way to build up a coherent combination of behavior overall. Now let's look at how the decorator design pattern is structured with a general UML class diagram. The component interface is used to define the common type for all the classes. A client class will expect the same interface across all the component classes. A concrete component class implements the component interface and can be instantiated. An instance of this class can be used as a base object in the stack. Decorator is an abstract class. Just like the concrete component class, it implements the component interface. The main differences are that decorator aggregates other types of components, which will allow us to stack components on top of each other, and decorator serves as the abstract superclass of concrete decorator classes that will provide an increment of behavior. We build the stack of components starting with an instance of the concrete component class and continuing with instances of subclasses of the decorator abstract class. In terms of our coffee analogy, the concrete component would be a black coffee. Decorators for our coffee would be milk, sugar, hot chocolate, and any other ingredient you could add to a coffee. There are many analogies that can be used for the decorator design pattern, from coffee to pizza, but these analogies don't translate well to how you would actually make use of this design pattern for software. So let's look at an example that is more realistic to what you would see in a software system. A web page is an example of where we would use this design pattern. A basic web page is simply a markup using HTML with style sheets and possibly some JavaScript. However, the behavior of a web page can be more complex. What if you want to make sure that people accessing your page are authorized? Or what if you want to split a large number of search results into separate pages? You don't want to write completely different web page types for every possible combination of web page permission, pagination, or caching behaviors. Instead, you can use the decorator design pattern to create one class for each type of behavior and build the specific combination of web page that you want at runtime. Let's take this example and see what it would look like in a UML class diagram by following the general design for a decorator design pattern. Your component interface is a web page. This will define all subclasses in the pattern as a type of web page, which have their own implementation of how to display themselves. The concrete component class is your basic web page. It consists of HTML, a style sheet, and scripts, which we will represent as strings for the sake of simplicity. This basic web page should know how to display all of its web page elements. Now, you need decorators to add more functionality to your basic web page using aggregation instead of subclassing the basic web page itself. You will need to use subtypes of the abstract web page decorator class to augment our basic web page. As we explored earlier, the web page decorator will be a subtype of web page. Therefore, a subtype of the decorator is also a subtype of the web page interface. You can define any number of additional behaviors you want to augment your basic web page with. In this example, we will enhance the basic web page by adding authorization to ensure the user can access the page, and authentication to make sure the user is who they claim to be. Can you see how this reduces the number of classes we would need to create? If you used inheritance of the basic web page, you would need to create a class for every combination of these behaviors. That means we would need a separate class for the combined authorization and authentication functions. The decorator design pattern addresses this problem by allowing concrete decorators to aggregate any type of component. Now, let's take a look at how we would implement this design. Step 1. Design the component interface. First, you define your interface that the rest of the classes in the design pattern will be subtypes of. The interface will define the common behaviors that your basic web page and decorators will have. Step 2. Implement the interface with your base concrete component class. Your basic web page will implement how it will display itself by using standard HTML markup and page element styling defined in the cascading style sheet. Your basic web page will also run some basic JavaScript. This will be the base building block for all web page objects during runtime. Step 3. Implement the interface with your abstract decorator class. The implementation of the decorator class is important despite how little code there is. The first thing to note is that a web page decorator contains only one instance of web page. This allows us to stack decorators on top of the basic web page and on top of each other. Each type of web page is responsible for its own behavior and will recursively invoke the next web page on the stack to execute its behavior. The constructor will let you link different subtypes of web page together in a stack. All you need to do is tell it what instance of web page subtype you want to stack upon. Since the constructor allows you to link any web page subtype onto the stack, the order in which you build the stack matters. The important part is that the basic web page must be the first one in the stack. The rest of the ordering will depend on the design of your system and which augmenting behaviors you want executed first. Your abstract decorator simply delegates the display behavior to the web page object that it aggregates. This will let you combine the display behavior down the stack of web pages. Step 4. Inherit from the abstract decorator and implement the component interface with concrete decorator classes. The constructors will use the abstract superclasses constructor, since it will allow us to stack the decorators together. Remember that the abstract web page decorator class handles the aggregation of the concrete decorator classes. Each decorator has its own responsibilities. You implement these responsibilities within the appropriate classes so that they can be invoked. In order to recursively call the display behavior, the concrete decorators invoke the superclass's display method. Since the abstract decorator superclass facilitates the aggregation of various types of web pages, the call to superdisplay will cause the next web page in the stack to execute its version of display until you get to the basic web page. The recursive call will end here because the basic web page is the concrete component, which does not aggregate any other types of web pages. The idea here is to link the calls of display all the way to the bottom and bubble the execution back up. This makes sense because you need to build your basic web page before you can add more behaviors to it. Now that you've completed your decorator pattern, let's see it in action. You build your basic web page first, add the authorization behavior next, and then complete the web page by adding the authentication behavior last. This way, when the display method is called, it will link the method calls down to the basic web page. The basic web page will display itself, and then the display call will move back up the links to the authorized behavior first and the authentication behavior last. The output of this program would look like this. If we refer back to our aggregation stack diagram, the invocation of display looks like this. As you can see, you can add any decorator to the basic web page to achieve a different combined behavior. This allows you to dynamically build up the behavior of your basic web page because we can instantiate and add new objects to the aggregated stack. The decorator design pattern is capable of letting you embellish your objects in a very unique way. To summarize, the key concepts for this design pattern are that we can add, in effect, any number of behaviors dynamically to an object at runtime by using aggregation as a substitute for pure inheritance. Polymorphism is achieved by implementing a single interface. Aggregation lets us create a stack of objects. Each decorator object in the stack is aggregated in a one-to-one relationship with the object below it in the stack. And by combining aggregation and polymorphism, we can recursively invoke the same behavior down the stack and have the behavior execute upwards from the concrete component object. Not only does the decorator design pattern let you dynamically modify objects, but it also reduces the variety of classes you would need to write. A larger code base not only takes more time to complete, but is also difficult to maintain and can reduce the flexibility of your system. You want to have a robust system, but without the headache of having an enormous amount of code to write and look after. Using design patterns like the decorator pattern will help you create complex software without the complex overhead. Hi, welcome to the second module. In the first module, you learned about a variety of creational and structural design patterns. In this module, you'll learn about behavioral design patterns. These patterns focus on ways that individual objects collaborate to achieve a common goal. By the end of this module, you'll have learned about some of the most useful design patterns you can apply to addressing design issues in your software systems. Enjoy! When designing software, it's important to recognize how your different objects work together towards a common goal. Each object you make is a piece of the larger solution. In order for each one to do its work effectively, it needs to have a set purpose. Think of it like each person working at a company. If the people of the company didn't have any predefined roles, there would be no way to make sure that each of their functions was being executed. The company would be less effective and not nearly as organized. This situation is like a behavioral pattern. Behavioral patterns also focus on how independent objects work towards a common goal. There are many ways that objects can have their behaviors defined. In this module, I will explain different behavioral patterns that you can use to design software. To get a better idea of how behavioral patterns can extend to the real world, let's look at some examples. Have you seen the directions on making soup or mixing a drink from powdered ingredients? They would both have similarly described steps to get a container, empty the ingredients into the container, add water, stir, and prepare. The steps are ordered the same way, with some identical steps and some different in implementation. Consider this example. Let's say you're an executive chef for a large chain of restaurants that serve pasta. You want the dishes to be consistent at all the restaurant locations in the chain, so you provide instructions for making each dish. Your two most popular dishes are spaghetti with tomato sauce and meatballs, and penne noodles with Alfredo sauce and chicken. Both dishes require that you boil water, cook the pasta, add the sauce, add the protein, and garnish the plate. Some of these steps are implemented differently, depending on what dish you're making. Each dish has a different protein, sauce, and garnish, so those would be implemented accordingly. Other steps would be implemented the same for both dishes. Both dishes require water to be boiled. Water can only be boiled a singular way, regardless of the type of dish being made. You can model this situation with a pasta dish class, with a method that makes the recipe for each subclass, spaghetti with meatballs or penne Alfredo. The method knows the general set of steps to make either dish, from boiling water to adding the garnish. Steps that are special to a dish, like the sauce to add, are implemented in its subclass. These are all elements of the template method pattern, which is the design pattern we will be talking about next. The template method defines an algorithm's steps generally, deferring the implementation of some steps to subclasses. It is a behavioral design pattern and is concerned with the assignment of responsibilities. Now it's your turn to come up with a template method. The name of your self-driving vehicle template method could possibly be drive to destination. Both a self-driving car and motorcycle would require such a function for reaching their destination. They would need to go through all the steps to get there. These steps would involve accelerating, steering, braking, and checking if they're at their destination. Calls to all of these methods would be laid out inside the template method. It would be called the same way for both subclasses, though some of the methods being called would differ. For example, how you steer a car is different from how you steer a motorcycle. The template method is best used when you can generalize between two classes into a new superclass. Think of it like another technique to use when you notice you have two separate classes with very similar functionality and order of operations. After you use generalization, you can more effectively reuse objects. Using inheritance, you can share the functionality between classes and allow for clearer and more self-explanatory code. Now let's take a look at how we might create the UML for the template method pattern. Let's go back to our pasta example. We have the pasta dish superclass with a template method makeRecipe, which calls other methods for the steps of the recipe. Some steps are common across specific dishes, like boiling water, so boil water is a method of pasta dish. However, some steps are special to the dish, like adding the sauce, so add sauce is an abstract method of pasta dish. It will be up to a subclass of pasta dish to provide the add sauce method body to add the right sauce. Spaghetti meatballs and penne alfredo are subclasses of the pasta dish class. They must provide their own versions of add pasta, add sauce, add protein, and add garnish. Now it's time to see some Java code on how you'd implement a template method. Let's take a look at the code for the pasta dish superclass. Pasta dish needs to be an abstract class. You can't create a generic pasta dish. You wouldn't know what pasta, protein, sauce, and garnish to add, so those methods are abstract. The make recipe method is our template method. You will notice that this method is marked as final. In Java, the final keyword means that the method declared cannot be overridden by subclasses. This means that neither specific dish subclass can have its own version of make recipe. This ensures consistency in the steps of making the dishes and reduces redundant code. From within make recipe, the other methods are called. For example, it calls boil water. Boil water is done the same for any subclass, and so its implementation is consolidated in the superclass. The methods add pasta, add protein, add sauce, and add garnish are going to be left up to the subclasses, like spaghetti meatballs or penne alfredo, to provide them. Before I continue, it's time for you to try writing the superclass of a template method. Now that I've gone over the pasta dish superclass and its template method, I will go over the subclasses. Let's take a look at what our spaghetti meatballs and penne alfredo subclasses look like. Both spaghetti meatballs and penne alfredo extend the pasta dish class. They each have to implement the abstract methods add pasta, add protein, add sauce, and add garnish to provide the suitable ingredients for the dish. The add pasta, add protein, add sauce, and add garnish methods are called in the make recipe template method found in the pasta dish superclass. The template method is inherited in a subclass and behaves as expected to make a dish with the right ingredients. Now you can try implementing template method subclasses. The template method can be helpful if you have two classes with similar functionality. When you notice two classes with a very similar order of operations, you can choose to use a template method. The template method pattern is a practical application of generalization and inheritance. When writing software, you might notice two separate classes that share similarities, like each having a method with a very similar algorithm. Rather than making changes to these algorithms in two places, you can consolidate the algorithms to one place, within a template method of a superclass for the two classes. You generalize from two separate methods into one template method within the superclass, which would be inherited by the two classes. The differences in the algorithms would be done through calls to abstract methods, whose implementations are provided by the subclasses. In this lesson, we will talk about another type of design pattern called the chain of responsibility design pattern. The chain of responsibility is what it sounds like, a chain of objects that are responsible for handling requests. Think of it like requesting help on a health problem. So you try visiting your doctor first with your request. But your case is unusual, so you're referred to a specialist. But the specialist is on leave and can't take your request, and so you're referred to another specialist. And finally, this specialist ends up dealing with your problem. You don't care who along this chain of health professionals actually helps. You only care that your request is met. In software design, the chain of responsibility is a series of handler objects that are linked together. These handlers have methods that are written to handle specific requests. When a client object sends a request, the first handler in the chain will try to process it. If the handler can process the request ends at this handler. If the handler cannot deal with the request, the handler will send the request to the next handler in the chain who will try to process the request. Again, if the handler cannot process the request, it will send the request on to the next handler. This passing of the request continues until we find a handler that can process the request. If the request goes through the entire chain of handlers and no handler can process it, then the request is not satisfied. Let's look at an example of this. Say you were fixing a chair and you needed a tool to tighten a particular screw. You're not sure which type of tool to use. You have several types of screwdrivers and wrenches. What would you do? You would probably take each tool and, one at a time, try it on the screw until one of them works. This is very similar to how the chain of responsibility design pattern works. Each object tries to handle the request until one is able to successfully handle it. You can also think of this pattern as similar to exception handling in Java. With exception handling, you write a series of try-catch blocks in your software to ensure that exceptions are dealt with properly. When an exception occurs, one of the catch blocks is expected to handle it. Where might you use this design pattern in your software? The chain of responsibility can be used for many different purposes. Suppose you are setting up an email service where there are lots of ways to filter through the emails. An email message is considered by a series of filters until one is found that applies. You can create objects that work as the individual filters. Each of these filter objects has a method that I will call handleRequest. This method will check if a filter's particular rule matches an email message's content. If the rule matches the content, it will deal with the email. For example, the filter object can put that email into a spam folder, and the request is done. If the rule doesn't match the content, then the filter will call the next filter in the chain to handle the request. Using the chain of responsibility design pattern is a very common way to set up this kind of behavior. In general, the UML class diagram for the chain of responsibility design pattern looks like this. All the objects on the chain are handlers that implement a common method handleRequest, declared in an abstract superclass handler. These handle objects are connected from one to the next in the chain. There are subclasses of handler to handle requests in their own way. Can you see an issue with the design? What if, for example, there's a mistake in the second filter? What if its rule doesn't match but forgets to pass the request on to the next filter? Then the handling ends prematurely. This is a problem with the chain of responsibility. We need an algorithm to make sure that each filter class handles requests in a similar fashion. That is, we want to make sure that each filter goes through the following steps. First, check if a rule matches. If it does match, do something specific. If it doesn't match, call the next filter in the list. To achieve this, you can use the template pattern that you learned from an earlier lesson to ensure that each class will handle a request in a similar way, following the required steps. Often, design patterns can have their own internal problems, and you can use other design patterns to fix those problems. It is very common in software design to combine patterns. The chain of responsibility is a very important pattern to learn in software. The intent of this design pattern is to avoid coupling the sender to the receiver by giving more than one object a chance to handle the request. Whoever sends the request doesn't have to care who will handle the request. It just sends it to the first thing, and hopefully someone will take care of it. This decouples the sender and receiver from each other. All the sender cares is that there is a handler for the request. It doesn't care which handler actually services the request. This implementation makes it very easy for the sender. For a real-life example of this design pattern, let's use a company bureaucracy. You're requesting donations for a worthy cause, so you ask one of the employees. But they can't authorize such a donation, so your request goes to their manager. But the manager doesn't have the budget to donate, so your request goes to a director. The director is not fully convinced of the cause, but passes it up the chain to the president. Finally, the president decides to authorize a big donation to your request. Congratulations! As you've seen, the chain of responsibility design pattern is a very useful pattern that can help decouple classes and deal with situations in which streams of different requests need to be handled. When you come across this issue, try and think of how you can apply the chain of responsibility. It won't be easy at first, but after some time in practice, recognizing where and when you need to use this design pattern will come naturally. Good luck! Think about what you're doing right this very second. You're obviously watching this lesson, but what else are you doing? Are you sitting? Standing? Laying down? Let's say I asked you to do a dance, but remain in the same state. If you're sitting down, your dance might involve you waving your arms and shoulders and bobbing your head. If you're standing, you would be able to add some footwork to your dance. If you're laying down, you might throw your hands in the air and wiggle your body. All I had to do was tell you to dance, and you chose a dance that was applicable to your current state. I didn't have to specify what your dance should look like. If I had told you to tap dance, which is a dance that requires you to tap your feet on the ground, that would be difficult if you were in a lying down state. Likely, you would have had to change your state in order to complete that action. Since the objects in your code are aware of their current state, you can use this premise in your code. They can choose an appropriate behavior based on their current state. When their current state changes, this behavior can be altered. This is the state pattern. So when should you use the state pattern? The state pattern is primarily used when you need to change the behavior of an object based upon the state that it's in at runtime. Let's look at an example. A vending machine represents the state pattern well, since it has several states and specific actions based on those states. Let's say I wanted to purchase a chocolate bar from a vending machine. The chocolate bar costs $1. I walk up to the vending machine, insert my dollar, and make my selection. The machine then dispenses the chocolate bar. I take the chocolate bar and go on my merry way. This would be the typical case for this scenario, but let's explore some other situations that could happen. What if I walked up to the vending machine, inserted my dollar, and then decided I didn't want the chocolate bar anymore? I would press the eject money button, and the machine would return my dollar. What if the vending machine runs out of chocolate bars? The vending machine needs to be keeping track of its inventory and notifying the customers when there is no more of a particular product left. If I represent this as a UML state diagram, it would look like this. From this diagram, you can see that there are three states: idle, has $1, and out of stock. The vending machine is in one of these states at a time. You can also see that there are three triggers, or events. These triggers would be insert dollar when a dollar is inserted, eject money when there is a request to eject money, and dispense when there is a request to dispense a product. There are two actions that the vending machine can do. These actions are do return money or do release product. Let's see what this might look like in code. My vending machine class would look like this. Take a second and think about the different states that the vending machine could be in. Before I approach the vending machine is in an idle state. Nothing is happening. What happens when I insert my dollar? The state of the vending machine changes. There are events to respond to and actions to perform that are now relevant to the vending machine. These would be responding to an eject money request by returning my money, and responding to a dispense request by releasing a product. A third state the machine could be in would be if the machine is out of stock. It would no longer be able to dispense a product, so how to respond has changed. Let's take a look at one way we can represent this in Java. First, we'll make some singleton state objects. We define our three states as new state objects. State.idle would denote the idle state, state.has$1 would denote the machine having $1, and state.outofstock would denote the machine is out of stock. Our vending machine class would look like this in part. Current state refers to a specific state object, whichever denotes the current state of the vending machine. When the machine is instantiated with a stock count greater than 0, the current state is set to state.idle. If the stock count is not greater than 0, the current state is set to state.outofstock. Now, if we look at what happens when I insert a dollar, you can see that if the current state of the vending machine was state.idle, then the current state changes to state.has$1. If the current state of the machine was already state.has$1, my money is returned and the current state is set to state.idle. If the current state of the machine was already state.outofstock, my money is returned and the current state stays in state.outofstock. But these state objects seem pretty passive and don't have much responsibility themselves. Let's now look at how you can restructure this properly using the state design pattern. We will define a state interface with a method for each trigger that a state needs to respond to, that is, insert dollar, eject money, and dispense. And we'll have state classes that implement the state interface, one for each state needed, that is, idle state, has $1 state, and out of stock state. This is the state interface. State classes must implement the methods in this interface to respond to each trigger. Next, our idle state class would look like this. Our idle state class now implements the state interface. When a dollar is inserted, the insert dollar method is called, which then calls a set state method upon the vending machine object. This changes the current state of the machine to the has $1 state. Similarly, in the has $1 state class, when the eject money method is called, the money is returned, and set state is called on the vending machine to change the state to the idle state. Here's what happens if the dispense method is called in the has $1 state class. The product is released. Depending on whether stock remains after releasing the product, the vending machine's current state is set to either the idle state or the out of stock state. The vending machine class constructor will instantiate each of the state classes, and the current state will refer to one of these state objects. The vending machine class would also have methods to handle the triggers as before, but now delegates the handling to the current state object. Notice now how much cleaner the code is without having long conditionals in these methods. The structure of the state pattern generally looks like this. In our example, the vending machine is the context class. It keeps track of its current state. When a trigger occurs and a request is asked of a context object, it delegates to a state object to actually handle the request. The state pattern is useful for when you need to change the behavior of an object based upon changes to its internal state. You can also use the pattern to simplify methods with long conditionals that depend on the object's state. In this lesson, we will talk about another type of design pattern called the command pattern. The command pattern encapsulates a request as an object of its own. Usually, when one object makes a request for a second object to do an action, the first object would call a method of the second object, and the second object would complete the task. In this situation, the sender object directly has to communicate with the receiver object. Instead of having these objects directly communicating with each other, the command pattern creates a command object in between the sender and receiver. This way, the sender doesn't need to know about the receiver and the methods to call. Think of it like how a boss in a company uses memos to carry out tasks. For example, if the boss needed a worker to schedule a meeting and also needed another worker to talk to an important client about business, the boss can use memos. The boss is a very busy person and may not have time to remember which workers do what jobs, and won't have time to walk to the different workers to ask them to complete the tasks. Instead, the boss could just write the tasks down onto a sticky note, and a secretary could give these to the workers that can complete them. The boss is encapsulating his commands into memos, the way requests could be encapsulated into command objects in software. So, you may have noticed in the previous example that if a boss creates a memo, there needs to be some sort of secretary that gets these memos to the actual receiver to get this memo completed. Similarly, in software, a sender object creates a command object, but what actually makes the command object do what it's supposed to do and invoke the specific receiver object to complete the task? This is where an invoker comes in. The command pattern has another object that invokes the command objects to complete whatever task it is supposed to do, called the invoker. A command manager can also be used, which basically keeps track of the commands, manipulates them, and invokes them. Think of the invoker like the secretary in the company example. The secretary keeps track of the memos, making sure that the memos are executed at the right time. So, where can you implement the command pattern in your software? There are many different purposes for using the command pattern. One purpose of using the command pattern is to store and schedule different requests. When an object calls a method of another object, you can't really do anything to the method calls. Turning the different requests in your software into command objects can allow you to treat them as the way you would treat other objects. You can store these command objects into lists. You can manipulate them before they are completed, or you can put them onto a queue so that you can schedule different commands to be completed at different times. For example, you can use the command pattern to have an alarm ring in calendar software. When an event is created in the calendar, a command object could be created to ring the alarm. This command could be put onto a queue so that the command can be completed later when the event is actually scheduled to occur. Another important purpose of the command pattern is allowing commands to be undone or redone, like how you can undo or redo edits in a document. This example will be easier to understand by using a diagram. Suppose that you are creating text editing software. There can be many different commands that can be executed in your text editing software, like delete text, change font, paste text, and so on. To achieve redo and undo functionality, your software will need two lists: a history list, which holds all the commands that have been executed, and a redo list, which will be used to put commands that have been undone. Every time a command is requested, a command object is created and executed. Every time a command is completed, that command goes to the history list. Now, what if the user wanted to undo a command? Well, the software would look at the history list and look at the most recent command executed. The software would ask this command to undo itself, and then put it on the redo list. Let's undo another command. If the user needs to redo, the software would take the most recent command undone in the redo list and ask the command to execute again, then move it onto the history list again. Let's redo another command. The redo list will also need to be emptied every time a command is executed, because usually you can't redo a previous edit after a new edit has already been made. So that's how you can use the command pattern to create your text editing software. This redo-undo functionality doesn't have to be just for text editors. You can use the command pattern to allow redo-undo on any type of application. The important thing is that the command pattern lets you do things to requests that you wouldn't be able to do if they were simple method calls from one object to the other. You can store these commands in a log list also, so that if your software program has an unexpected crash, you can allow your users to redo all the recent commands. Creating these requests as objects allows you to create very useful functionality in your software programs. How might the command pattern look in a UML diagram and in your source code? Here's how it would look in a UML diagram. You have a command superclass, and all commands will be instances of subclasses of this command superclass. Superclass defines the common behaviors of your commands. Each command will have the methods execute, unexecute, and is reversible. The execute method will actually do the work that the command is supposed to do. Unexecute will do the work of undoing the command, and isReversible determines if the command is reversible, returning true if the command can be undone. There could be some commands that can't be undone. For example, save is a command that doesn't really make sense to be undone. You can't really unsave a work that has been saved. These concrete command classes will call on specific receiver classes to deal with the actual work of completing the command. If we look into more details of concrete command class, for example, pasting text, we can see how a command object should be. We can see that the paste commands extends the command superclass. The paste command object also keeps track of where the text will be inserted and what will be inserted. This is a very important aspect of command objects. They must keep track of a lot of details on the current state of the document in order for commands to be reversible. In this case, the paste command is also a reversible command because you can delete the object you just pasted, so it will return true if isReversible is called and must keep track of where the text was pasted. When the execute and unexecute methods are called, this is where the command object actually calls on the receiver, which in this case is the document, to actually complete the work. The source code for the invoker is done in simple steps. First, it will need a reference to the command manager, which is the object that manages the history and redo lists. The invoker then creates the command object with the information needed to complete the command, then calls the command manager to execute the command. There are many benefits that come from using the command pattern. As I've mentioned before, it allows you to manipulate the commands as objects the way you could not do with method calls. Working with command objects allows you to add the functionalities I mentioned earlier, like putting commands into queues and adding an undo-redo function. Another main benefit of the command pattern is that it decouples the objects of your software program. When you have a class that wants to make a request, that class doesn't need to know about the other objects in the software system. It can simply just create a command object and let the command object deal with the work by invoking the receiver objects, like with the boss memo example I mentioned earlier. The object doesn't need to know who deals with the request anymore, like how the boss doesn't need to know which worker will deal with the task. The command pattern also allows you to pull out logic from your user interfaces. Usually, code to handle requests is put into the event handlers of user interfaces. However, it doesn't really make sense to have a lot of application logic sitting in your user interface classes. The user interface classes should only be dealing with user interface issues, like getting information to and from the user. Instead, the command pattern creates a new layer, which is where these command objects will go. Every time a button is clicked, it will create a command object instead, and that is where the logic will sit. These command objects are independent of your user interface, so it makes adding changes like new buttons to your software's user interface easier and faster. You can turn each and every service in your system into an object of its own, and allow much more flexible functionality. Next time you're creating an application, try applying the command pattern. Soon you'll see that using this pattern can really make your software programs versatile and easier to maintain, and you'll want to use it on every software you create. Good luck! Imagine that you have a favorite blog. Every day you visit it, multiple times per day, to check for new blog posts. After a while, you get fed up with this routine. There must be a better way, you think to yourself. The first solution that crosses your mind is to write a script to check the blog for new posts every fraction of a second. But upon further consideration, you realize most sites would not appreciate this barrage of requests and would block your IP address. To avoid this, you instead write a script to check the blog for new posts once per hour. But to your disappointment, this means that you're now missing out on blog posts that provide live changes, such as real-time posts about your favorite TV show. A better solution to this problem is for the blog to notify you every time a new post is added. You would subscribe to the blog. Every time a new post was published, the blog would notify each subscriber, including you. This way, you would be notified of the new content when it is created, rather than having to poll for this information at some interval. The subject, in our example the blog, would keep a list of observers. In this example, we might think of these observers as subscribers to the blog. The observers rely on the blog to inform them of any changes to the state of the blog, such as when a new blog post is added. Before we formalize this design pattern, let's explore how we could apply this idea to our example. First, we'll have a subject superclass that defines 3 methods: allow a new observer to subscribe, allow a current observer to unsubscribe, and notify all observers about a new blog post. This superclass would also have an attribute to keep track of all the observers, and will make an observer interface with a method so that an observer can be notified to update itself. Next, the blog class will be a subclass of the subject superclass, and the subscriber class will implement the observer interface. These design elements are essential to forming a subject and observer relationship, for example, for the blog and subscriber. In a sequence diagram that applies an observer pattern, there are two major roles, the subject and the observer, which in our example are played by a blog and a subscriber. In order to form the subject and observer relationship, a subscriber must subscribe to the blog. Next, the blog needs to be able to notify its subscribers that a change has happened. It's the job of the notify function to keep all of the subscribers consistent. This method is only called when the blog has a change, ready for its subscribers to know about. After the blog has a change, it's time for the blog to notify its subscribers through an update call, and the subscribers to get the state of the blog through a getState call. It's up to the blog to make sure its subscribers get the latest information. If the subscriber does not end up enjoying the content of the blog, they would need a way to unsubscribe. That is the last call in the sequence diagram. It originates from the subscriber and lets the blog know the subscriber should be removed from its list of subscribers. This is the core behavior for the observer design pattern, and essential for our subscriber to be able to subscribe to a blog they like. Now that we've applied the observer pattern to a specific example, let's take a look at how this idea can be abstracted into a design pattern, as given by the following UML diagram. In this UML class diagram, the subject superclass has three methods: register observer, unregister observer, and notify. These are all essential for a subject to relate to its observers. Specifically, the blog subclass of subject would inherit these methods to subscribe, unsubscribe, and notify its subscribers. The observer interface only has the update method. An observer must always have some way to update itself. Without the ability to be told to update, an observer wouldn't be informed of changes in the subject. The subscriber class implements the observer interface, providing the body of an update method so a subscriber can get what changed in the blog. Note that a subject may have 0 or more observers registered to it at any given time. Now it's time to take a look at some Java code for the observer pattern. Let's see what the code for the subject superclass looks like. The register observer method adds an observer to the list of observers. The unregister observer method removes an observer from the list, and the notify method calls an update upon each observer on the list. Next, the blog class is a subclass of subject, which will inherit the register observer, unregister observer, and notify methods, and have the other responsibilities of managing a blog and posting messages. Now that I've gone over the subject superclass, let's take a look at the observer interface. The observer interface makes sure all observer objects behave the same way. Observer classes only need to implement a single method, update. The update method is called by the subject. The subject makes sure when a change happens, all its observers are notified to update themselves. More specifically, for our example, we have a class subscriber that implements the observer interface. This update method is called when the blog notifies the subscriber of a change. The observer design pattern can save you a lot of time when you're implementing your system. If you know that you have many objects that rely on the state of one, the value of the observer pattern becomes more pronounced. Instead of managing all the observer objects individually, you can have your subject manage them and make sure the observers are updating themselves as needed. There are many different ways and situations you can apply the observer design pattern. As a behavioral pattern, it makes it easy to distribute and handle notifications of changes across systems in a manageable and controlled way. Welcome to the third module in this course. So far, you've learned about creational, structural, and behavioral design patterns. In this module, you will learn about the MVC, or Model View Controller, design pattern. This is a pattern that builds upon design patterns that you've learned about in the first two modules. You will also learn about several general design principles that underlie the design patterns to achieve software that is reusable, flexible, and maintainable. You will then move on to learn about ways to analyze and critique your code for bad design. You will learn about many common malpractices and why they lead to bad design. In the software industry, these are often referred to as anti-patterns or code smells. By the end of this module, you'll have the knowledge that you need to tackle the remaining capstone assignments for this course. So let's get started. Imagine you are hired by a small grocery store in your neighborhood. Their cashiers are complaining about the old-style cash systems where they have to manually type out the price of each and every item. At the same time, the customers are starting to get tired of waiting in line for purchases to be made this way. What they need is a system for entering and displaying orders. In other words, a user interface. The customer and the cashier should see the items that are entered into the order using a barcode scanner. They should also be able to see the total bill amount. Cashiers will like it because they don't have to type in prices anymore, and customers will like it because orders get done faster, and they can see the item prices on the screen. If mistakes are made, the cashier can easily make corrections, and everyone is happy. Anytime you hear user interface, you should consider using an MVC pattern. MVC stands for Model, View, Controller. The MVC pattern divides the responsibilities of a system that offers a user interface into those three parts. Let's look at a diagram of a simple MVC pattern. First, let's talk about the model. The model contains the underlying data and logic that users want to see and manipulate. In this case, the cashiers and customers want to be able to put together grocery orders. A key part of the MVC pattern is that the model is self-contained. It has all of the state, methods, and other data that it needs to exist on its own. Next up is the view. The view is just like it sounds. It gives a user a way to see the model, or at least parts of it. At the grocery store, this would be the screen that shows a list of items and their prices. Sometimes, the view will also have interaction elements like buttons and fields that allow the user to interact with the system. While the model is the back end, the underlying software, the view is more like the front end, the presentation layer. Although our example will only have one view, it is possible to have several views all used within the same model. When some value changes in the back end, or the model, it has to tell the view to update itself accordingly. This is done by using the observer design pattern. Remember, in the observer pattern, the observers act like subscribers. In this case, any view is also an observer. When the model changes, it notifies all of the views that are subscribed to it. The view may also have ways for a user to make changes to the data in the underlying model. If you were a cashier at a grocery store, in what ways could you change the order? Well, you could delete items if customers change their mind, or change the prices of items to make corrections. You've probably seen buttons for these actions. In the MVC pattern, the view does not directly send requests to the model. Instead, information about the user interaction is passed to a controller, which is responsible for interpreting these requests and changing the model. This way, the view is only responsible for the visual appearance of the system, and the model focuses solely on managing the information for the system. Thus, the MVC pattern basically uses the separation of concerns design principle to divide up the main responsibilities in an interactive system. In general, the model corresponds to those entity objects derived from analyzing the problem space for the system. A view corresponds to a boundary object at the edge of your system that deals with users. A controller corresponds to a control object that receives events and coordinates actions. Think about the cashiers at the grocery store. The model could be very complex, but let's use a simplified version. This store order model will simply be a grocery list with prices and a few methods to modify the order. The view will display the list of items with their prices and the total price. The cashier would like to be able to fix mistakes too, so let's include two buttons we talked about, delete item and change price. Let's follow what could happen when the change price button is pressed. The cashier presses the change price button. An event handler for this button calls the controller. The controller reads a new price from a text field on the view and uses these two pieces of information, the item to be changed and the new price, to request a price change in the model using a method in the model. The controller could also check that the price is valid and ask the view to clear the text box. The model has now changed the price of one of the items. Since the view is an observer of the model will notify the view that it has changed, and the view will update itself. The cashier's display now shows the new price. So, how is this implemented? Let's start with the most essential part, the model. The model should be able to exist on its own, with no views or controllers. Of course, you will probably use views and controllers to see and change the model, but the model should not rely on a view or controller to exist. Since our view is going to be an observer, we have to make the model an observable. We will use the java.util package to implement this behavior. Java.util contains an observable class that you can extend. If you import java.util and then extend observable, your store order class will allow you to add your views as observers. That way, they will act like subscribers of the store order and update whenever an order is updated. This class has several methods that modify itself. You can add items, delete items, and change prices. Of course, a real order model will probably have more, but these basic functions are a good start. Notice that our model doesn't have any user interface elements and is not aware of any views. It will update the views through the observer pattern. Whenever changes are made, the setChange method flags the change, and the notifyObservers method notifies the views so that they can update themselves. Let's have a look at one of these views. Since your OrderView class implements the observer interface, you must provide an update method. Notice that you had to downcast your store order in order to get the getItemList and getPriceList methods. If you would like to make your code more type-safe, you could develop your own observer pattern with generics. What happens when we use the view to modify the model? Look at the event handling here. Notice that nothing here calls a method of the model. Instead, they call methods of the controller. The controller might look something like this. In this example, the controller is very simple, but there are still a few things we can learn. The controller must have references to both the view and model that it connects. Crucially, the controller does not make changes to the state of the model directly. It calls methods of the model to make changes. Using a controller makes the code better in a few ways. First of all, the view can focus on its main purpose, presenting the user interface. The controller takes the responsibility of interpreting the input from the user and working with the model based on that input. Separating these concerns makes the code cleaner and easier to modify. Secondly, with a controller in between the model and the view is no longer tightly coupled to the model. While you are developing, you might add features to the model and test them long before putting them in the view. Like other design patterns, there is no one way to use the MVC pattern. You may find that your program needs a bit of a different approach. The defining feature of the MVC pattern is the separation of concerns between the backend, the front end, and the coordination between the two. While our example had one class each for the model, view, and controller, software systems will generally have multiple model classes, view classes, and controller classes. You will find the model view controller pattern in just about any application with a user interface. Let's review the components. The model contains the underlying data, state, and logic that the user wants to see and manipulate. The view presents the model information to the user in the way they expect it and allows them to interact with it. A model could have several views that present different parts of the model, or present the model in different ways. And the controller interprets the user's interaction with elements in the view and modifies the model itself. The controller ensures that the views and the model are loosely coupled and allows the view to be mainly concerned with user interface concerns. Separating these functions makes the code easier to develop, read, and maintain. This separation of concerns allows your program to be modular and loosely coupled. Loose coupling is especially important in large development teams. One team of developers may be working on the front end, the user interface or views, while another team works on the back end, the model. Even if you're coding a project on your own, separating these will allow you to focus on each set of responsibilities separately. You can more easily replace the views to use a different user interface toolkit, while keeping the model the same. As a software developer, you should strive to create systems that are flexible and reusable. Flexible code bases allow for easier extension of the system. Reusable code means that you don't need to re-implement something that's already been done. Achieving both of these goals will help to make your code more maintainable. The design patterns that you've learned during this course are all different techniques you can use to help you write flexible and reusable code. They are a means through which you can improve the quality of your code. All design patterns follow a basic set of design principles, which address issues such as flexibility and reusability. One of these principles is called the open-closed principle. This principle states that classes should be open for extension, but closed to change. Now, what does that mean? As the name of this principle suggests, there are two parts to it, open or closed. Let's examine what each part means. You should consider a class as being closed to editing once it has been tested to be functioning properly. The class should be behaving as you would expect it to behave. All the attributes and behaviors are encapsulated. And proven to be stable within your system. The class or any instance of the class should not stop your system from running or do any harm to it. The closed portion of the principle doesn't mean that you can't go back to a class to make changes to it during development. It's expected for things to change during the design and analysis phase of your development cycle. Changes to your classes are expected at that stage. Once you've reached a point in development where you've already finalized most of your design decisions and have implemented most of your system, then you should consider closing your classes. During the lifetime of your software, certain classes should be closed to avoid introducing undesirable side effects. Of course, you should still fix a closed class if there are any bugs or unexpected behaviors occurring. So, what do you do if you need to add more features? How do you extend your systems? This is where the open part of the design principle comes in. There are two different views of the open part of the principle, but they both view a class to be open if you can still build upon it. There are two different ways to extend your system using the open principle. The first way is through inheritance of a superclass. The idea is that when you want to add more attributes and behaviors to a class that is considered closed, you can simply use inheritance to extend it. This way, your subclasses will still have all the original functions of the superclass, but now you can add extra features in the subclasses. This helps preserve the integrity of the superclass, so that if you don't need the extra fluff of the subclasses, you still have the original class to use. Remember that subclasses can also be extended, so you can use the open-closed principle to continually extend your system as much as you want. You may reach a point where you no longer want a class to be extendable, in which case you can declare a class to be final, which will prevent further inheritance. The keyword final can also be used on methods. The second way a class can be considered open to extension is if the class is abstract and enforces the open-closed principle through polymorphism. An abstract class can declare abstract methods with just the method signatures. Each concrete subclass must provide their own implementation of these methods. The methods in the abstract superclass are preserved, and you can extend your system by providing different implementations for each method. This can be useful for behaviors that can be accomplished in different ways, like sorting and searching. You can also use an interface to enable polymorphism, but keep in mind that with an interface, you won't be able to define a common set of attributes. The open-closed principle is used to keep the stable parts of your system separate from the varying parts. While you want to be able to add more features to your system, you don't want to do it at the expense of disrupting something that works. By using extension over change, you can work on the varying parts without introducing unwanted side effects into the stable parts. Varying parts of the system should be kept isolated from each other. Since these extensions will eventually become stable and become integrated into your production, there's no guarantee that they'll all be completed at the same time. Some features and behaviors may be more complex than others. Some may be larger and more ambitious, or some may be discarded completely due to time or financial considerations. Isolating varying subsystems from each other can also prevent unwanted side effects from occurring when you're implementing them. All design patterns use the open-closed principle in some form. They all follow the idea that some part of your system should be able to extend and to be built upon through some means like inheritance or implementing an interface. The open-closed principle is a concept that helps keep a system stable by closing classes to changes, and allows a system to be open for extension through the use of inheritance or interfaces. It may not always be possible to practice this principle, but it's something you should strive for. Having a reliable and robust system is something you want to have. You want to build featureful systems, but you also want them to have good performance. A flexible and reusable codebase plays a key part in providing that. Design patterns are used to address specific software problems, but they all rely on a set of unifying ideas. The open-closed principle is one of those ideas that is used by design patterns, and is also a principle you should use when designing and building your software solutions. A common problem that you'll need to address when designing your systems is dependency. There are several questions that will arise when it comes to this topic, such as, where are my points of dependency? And to what degree is my system or subsystems dependent on a particular resource? Software dependency is essentially coupling, which defines how much reliance there is between different components of your software. If a part of your system is highly coupled, then the degree to which they rely on one another is considered high, whereas low dependency means that your system has a lower degree of coupling. For a review on coupling, you can check out the lesson on cohesion and coupling from Course 1. Dependency is an important topic because it will determine how easily you can make changes to your system. Think about it this way. If you were dependent on a specific type of food for survival, then you wouldn't be able to substitute it for something else. In a real-life example, our bodies are dependent on water for survival. We cannot replace water with bread and hope to get the same results as if we were drinking water. You'll end up facing the same issue in software. Trying to substitute one class or resource for something else is not easily done, or sometimes even possible. This is because your system is dependent on a specific function that may only be offered by that particular class. To address this issue, we use the dependency inversion principle, which will help you make your systems more robust and flexible. The principle states that high-level modules should depend on high-level generalizations, and not on low-level details. This means that your client classes should depend on an interface or abstract class instead of referring to concrete resources, and that your concrete resources should have their behaviors generalized into an interface or abstract class. The idea is that interfaces and abstract classes are considered high-level resources, while a concrete class is considered a low-level resource. An interface or abstract class defines a general set of behaviors, and the concrete classes provide the implementation for these behaviors. This way, your client classes can be independent of low-level functionality. All the design patterns that we've introduced are built on this principle. Let's take a look at the difference between low-level dependency and high-level dependency to demonstrate how the dependency inversion principle works. In a conventional software design, your system architecture might look like this. Your subsystems are directly dependent on each other, which means that your client class will directly reference some concrete class in your enterprise subsystem, which will directly reference some concrete class in your backend. This form of dependency is called a low-level dependency because the client classes are naming and making direct references to a concrete class. But what happens when you need to change this reference in the future? Here, you have direct naming and referencing to the concrete class called quick sorting, which you use to sort a list sent to your system by a user. The issue is that if you were to implement a different sorting class called merge sort, you would need to make significant changes to your client subsystem class. Notice that you've changed the type of sorting class from quick sorting to merge sorting, and you've also had to change the sorting method call. Imagine how much work you would need to do every time you want to make a sorting algorithm change to your system. Not only is it impractical, these kinds of changes could have unexpected side effects if you missed any old references. The dependency inversion principle addresses this issue by generalizing low-level functionality into interfaces or abstract classes, so that when alternative implementations are offered, they can be used with ease. When you use the dependency inversion principle, the overall architecture of your system will look very similar to the design patterns that we've explored. You need to generalize the behaviors across each subsystem into an interface. The concrete classes of each subsystem will then implement the interface. And finally, your client classes will make references to the interface, rather than directly to the concrete classes. As you can see, instead of declaring a concrete class, you can declare the sorting interface. Then you can determine which instance of sorting class you want the client subsystem to have during instantiation. Furthermore, since you can generalize the sorting behavior into a method called sort in the interface, you won't need to change the method call in the client subsystem. Since your client class is dependent on a high-level generalization rather than a low-level concrete class, you can easily change which resource your client will be using. The generalization gives you a degree of indirection by allowing you to invoke behaviors in a concrete class through an interface. High-level dependency will prevent your client class to be directly coupled with a specific concrete class. This means that a client class is dependent on expected behaviors, not on a specific implementation of behaviors. Unlike in procedural languages, such as C, where calls are often made directly during a point in a program's execution, object-oriented systems don't always need to make method calls so directly. In fact, method calls in an object-oriented design should be done using a level of indirection. The dependency inversion principle suggests that you should make use of indirections by writing dependencies to generalizations, rather than directly to a concrete class. Just like with the design patterns we've looked at in this course, you'll want to use the dependency inversion principle during the design process. Since building a flexible, reusable, and maintainable system will prolong the life of your software, applying this design principle will help you achieve those goals. To summarize, the dependency inversion principle is a means to change the referencing of concrete classes from being direct to indirect, generalize the behaviors of your concrete classes into abstract classes and interfaces, have client classes interact with your system through a generalization rather than directly with concrete resources, and put emphasis on high-level dependency over low-level concrete dependency. Despite the extra work that may be required to design and implement your system, the amount of time and resources that you gain further down the road is worth the effort spent. Large systems are difficult to maintain, and when your system becomes too heavily coupled, changes will be hard to make. The dependency inversion principle will help you with insulating parts of your system from specific implementations of functionality. Just like with design patterns, you want to program to generalizations, like interfaces and abstract classes, rather than directly to a concrete class. It's a principle that you should follow in order to create a robust software solution. A common problem in object-oriented systems that design patterns attempt to address is how to reduce the amount of tight coupling. The design principles that are used by all the design patterns define different ways in which coupling can be managed. Less coupling in your system means that your system can be more flexible and is capable of handling changes to its existing codebase, such as the integration of new features. The design patterns that we have explored make heavy use of generalization, abstraction, and polymorphism as means of indirection. While inheritance is a great way to achieve a high amount of code reuse, it comes with the cost of tightly coupling the superclass with its subclasses. So why is there coupling? Think about what inheritance does in object-oriented programming. When a subclass inherits from a superclass, the subclass will gain knowledge and access to all of the superclass's attributes and methods, as long as their access modifiers are not private. This means that if you have multiple levels of inheritance, a subclass at the bottom of the inheritance tree can potentially have a way to access attributes and behaviors of all the superclasses. So what can we do to avoid this? You can use the composing objects principle to gain a high amount of code reuse without using inheritance. This principle states that classes should achieve code reuse through aggregation rather than inheritance. Design patterns, such as the composite design pattern and decorator design pattern, use this design principle. Both of these patterns compose concrete classes in order to build more complex objects at runtime. The overall behavior comes from the composed sum of the individual objects. An object can reuse and aggregate another object to delegate certain requests to it. The idea is that you want to design your system so that concrete classes can delegate tasks to other concrete classes. Delegation will provide a looser level of coupling than inheritance. The benefits are clear, but there is a disadvantage to using the composing objects principle. Let's take a look at the advantages first. We have already discussed the primary advantage of the composing objects principle, which is that aggregation and delegation offer less coupling than inheritance. Since the composed classes don't share attributes or implementations of behaviors, they're more independent of each other. They have an arm's length relationship, which allows for changes to be made easier. In inheritance, all subclasses of a superclass are tightly coupled to that superclass. How your classes will compose themselves is determined during the design phase of your development. In the UML class diagram on the left, objects can be composed recursively and uniformly, while on the right, an object is composed of others that have a consistent type. Composing objects also provides your system with more flexibility. During the design phase, it's easier and more natural to keep classes separated. Composing objects does not force you to try and find commonalities between two classes and couple them together like with inheritance. Instead, you're able to design classes that can work together without having to share anything between them. This flexibility will also help you if the system requirements change. If you use inheritance, you may have to restructure your inheritance tree. Finally, composing objects allows you to, in effect, dynamically change the behaviors of objects at runtime. You can build up a new overall combination of behavior by composing objects. With inheritance, the behaviors of your classes are defined during compile time, which means that while your program is running, they cannot change how they behave. There are an overwhelming number of advantages that composition has over inheritance, but you need to keep in mind the disadvantages as well. The biggest drawback of composition is that you must provide implementations for all behavior without the benefit of inheritance to share code. This means that you might have very similar implementations across classes. With inheritance, you don't need to provide each subclass with their own implementation of a shared behavior. The common implementation is simply accessed within the superclass. Needing to provide implementations for every class means that it will take time and resources. A programmer working on providing multiple implementations of the same behaviors means you'll have one less programmer working on other features. The composing objects principle has many advantages over using inheritance to reuse code and build up behaviors in a flexible way. This design principle will help you with reducing coupling in your system by using delegation and by composing objects with each other. In summary, the composing objects principle will provide a means of code reuse without the tight coupling of inheritance, allow objects to dynamically add behaviors at runtime, and provide your system with more flexibility. This means less time needs to be spent on system updates. Now, it's not to say that inheritance should never be used. Composing objects and inheritance both have their place. Composing will give you better flexibility and less coupling while maintaining reusability, but that doesn't mean it should always be used over inheritance. You need to examine the needs of your system in order to determine which design principle is appropriate. Do you have a set of related classes or unrelated classes? What is a common behavior between them? Do you need specialized classes to handle specific cases, or do you simply need a different implementation of the same behavior? These are the different kinds of questions that you'll need to ask yourself when designing your software systems. By knowing what each design principle recommends, you will understand how to deal with the design issues you will come across. Many design patterns that we've explored use generalization of concrete classes. These generalizations are presented as interfaces for client classes to use to indirectly invoke the behaviors of the concrete classes. Design patterns do this so that client classes become less dependent on concrete classes, allowing for changes to be made more easily. Interfaces play an important role in object-oriented programming, so much so that you should strive to program to interfaces instead of concrete classes. However, an issue can arise if an interface contains too much. Can you think of any problems that this might cause? Consider this example. Imagine creating a system that represents the checkout area at a grocery store. In North American countries, there are two ways a customer can pay for their goods. They can approach a human cashier operating a till, or they can use the automated self-serve machines. The purpose between the two can be generalized with an interface. They both scan items that a customer wants to purchase, accept some form of payment, and dispense change when needed. But there are some behaviors that are not shared between the two of them. While an automated self-serve machine can perform work indefinitely, a cashier needs to eat, go on breaks, and leave at the end of their shift. Now, you can simply put these human behaviors into a concrete cashier class, but there's an issue with this design decision. A client class would not be able to use indirection to invoke these human behaviors, because they're not in the interface. But if your client class calls a method directly upon a cashier, it will become dependent on that concrete class. So then, are you forced to add these human behaviors into the interface? Or do you just accept that your system now has a low-level dependency and will just do extra work when you need to make changes? Luckily, you can use the interface segregation principle to tackle this issue so that you won't run into dependency issues or be forced to generalize everything into the interface. The interface segregation principle states that a class should not be forced to depend on methods it does not use. This means that any classes that implement an interface should not have dummy implementations of any methods defined in the interface. Instead, you should split large interfaces into smaller generalizations. So, how does this work? The iCashier interface does work for the human cashier class because all its behaviors are captured by the interface. But, as you can see, this design is not ideal because the self-serve machines should not need to clock in and out of work or take any breaks. You don't want to be forced to provide method implementations for the self-serve machine that don't fit the machine. These would essentially be dumb implementations that don't do anything, and these are not behaviors that a client class should expect or be able to ask a machine to do. So, we should apply the interface segregation principle and split the iCashier interface into two smaller ones. This will allow each interface to be more accurate with its description of expected behaviors, and it will allow you to pick and choose which correct combinations of interfaces a concrete class should implement. In this design, the old iCashier interface is split into a new iCashier interface and an iHumanWorker interface. The iCashier interface describes the general behaviors of a cashier, human or machine, and the iHumanWorker interface describes the general behaviors of an employee. The human cashier class can implement both interfaces, and the self-serve machine class would only need to implement the iCashier interface. This way, both of your concrete classes will only need to provide implementations for the interfaces that generalize their specific functionality. Interfaces are an integral part of object-oriented systems. They will help you reduce coupling by generalizing concrete classes. But just like with all object-oriented principles, you should strive to use them properly. While large interfaces are not a poor design choice, you need to examine them in the context of your system to decide if you need to split it up into smaller generalizations using the interface segregation principle. This design principle states that a class should not be forced to depend on methods it does not use, and interfaces should be split up in such a way that it can properly describe the separate functionalities of your system. Sometimes it isn't always clear how to properly segregate your interfaces, or to predict future changes in requirements that will need interfaces to be split up. Having a system with well-defined interfaces will help you to see these segregation points better. You should always strive to be as precise as possible when designing interfaces. Remember that they are descriptions of what parts of your system can do. And the better the description, the easier it will be to create, update, and maintain your software. To manage complexity, one idea is that a class should be designed so that it does not need to know about and depend upon almost every other class in the system. That would increase coupling and make your system harder to maintain. This naturally leads to the concept that classes should have a narrow view of what other classes it knows. By limiting which classes communicate with each other, you can enforce the principle of least knowledge on your system. This principle is also realized in a rule known as the law of Demeter. The underlying idea of this law is that classes should know about and interact with as few other classes as possible. This means that any class should only communicate with its immediate friends. These friends would be other classes that one class should only know about. This notion is a little bit more abstract than other design principles, but it is equally as important because it helps to reduce coupling and provide stability to your systems. The law of Demeter is actually composed of different rules, which we will examine, as well as how the law of Demeter can be violated. The rules in the law of Demeter are used to provide a guideline as to what kind of method calls a particular method can make. The first rule we will look at states that a method, M, in an object, O, can call on any other method within O itself. This rule is fairly simple and it makes logical sense. A method encapsulated within a class is allowed to call any other method that is also encapsulated within the same class. In this example, method M is allowed to call the method N, and both methods are part of the same class. The second rule states that a method, M, can call the methods of any parameter, P. Since a method parameter is considered local to the method, the parameter can be considered a friend, so methods in the class for the parameter can be called. The method M in your class O has a parameter P of type friend. The law of Demeter will allow method M to invoke any method of the friend class. The third rule of the law of Demeter is that a method, M, can call a method, N, of an object, I, if I is instantiated within M. This means that if a method makes a new object, then the method can use that new object's methods. The object is considered local to the creating method, the same way an object is considered local when it is a parameter. In this example, the method M creates a new local instance of the friend class. Since the friend object is a local to method M, you are allowed to call any method of the friend class. In addition to local objects, the fourth rule states that any method, M, in object O, can invoke methods of any type of object that is a direct component of O. This means that a method of a class can call methods of the classes of its instance variables. Since class O has a direct reference to the friend class, any method inside of O is allowed to call any method of class friend. The law of Demeter appears to be a complicated and abstract concept, but all the rules come down to the principle that you should not allow a method to access another method by reaching through an object. This means that a method should not invoke methods of any object that is not local. We have just looked at what the law considers to be a local object. These objects should be passed in through a parameter, or they should be instantiated within a method, or they should be in instance variables. This allows methods to directly access the behaviors of local objects. The term reaching through means that you need to use another object to pass along your request, or that you are using methods of objects that are considered outside your immediate friends. These conditions commonly occur when you have a chain of method calls to objects you shouldn't know about, or when you use methods from an unknown type of object that is returned to you from your local method call. This is an example of chaining method calls to an object that does not belong to you. The driver knows about the car class, but the engine of the car is not a component of the driver. Therefore, the driver should not be calling methods of the engine. You should not be accessing methods of objects that are not within your immediate circle friends. Think about it this way. When you drive a car, you don't issue individual commands to every component of the car. You should simply just tell the car to drive, and the car itself will know how to deal with its components. The other way you can reach through an object is when your method receives an object of an unknown type as a return value, and you make method calls to the returned object. Returned objects must be of the same type as those declared in the method parameter, those declared and instantiated locally in the method, or those declared in instance variables of the class that encapsulates the method. Again, this is because you do not know about the object prior to it being returned to you, so you shouldn't be using something you don't know about. This idea that you should only use returned objects that match the types of local objects is demonstrated in this example. This driver class knows about the car class, which is declared in an instance variable, and also vehicle rental stores, which is declared as a parameter. However, since it does not create a new instance of a motorcycle, your driver should not be able to operate that type of vehicle. Since you have specified that the type of vehicle the driver can use is a car, the driver should only be able to operate a car. This would be similar to someone who has never driven a motorcycle going into a store and renting one to drive around. This person doesn't know anything about motorcycles, so why should they be allowed to rent and operate one? The law of Demeter defines how classes should interact with each other. They should not have full access to the entire system, because this causes a high degree of coupling. According to the law of Demeter, a class should only interact with those that are considered its immediate friends. Classes should know as little as possible about your system as a whole. This will help reduce the amount of coupling and prevent unwanted effects from cascading through your entire system. The law of Demeter, otherwise known as the principle of least knowledge, creates a set of guidelines that will help you determine how your classes should interact. This design principle focuses more broadly on how method calls should be made, instead of on specific ways to structure the design of your system. According to this design principle, a method, M, of an object should only call other methods if they are encapsulated within the same object, encapsulated within an object that is in the parameters of M, encapsulated within an object that is instantiated inside of M, or encapsulated within an object that is referenced in an instance variable of the class for M. While the law of Demeter does help reduce coupling, it also means that you will need to spend more time when designing and implementing your system. Sometimes, it might not be feasible to always follow these rules due to limitations on your time and resources. Other times, some degree of coupling may be unavoidable, at which point you'll need to decide how much coupling is tolerable. When you're designing your systems, you should do your best to practice these design principles, as they will help you create more flexible, reusable, and maintainable systems. Sometimes, no matter how well you design your code, there are still going to be changes that need to be made. It's difficult, if not impossible, to get it right the first time. That's where refactoring comes in. Refactoring is the process of making changes to your code so that the external behaviors of the code are not changed, but the internal structure is improved. This is done by making small, incremental changes to the code structure and testing frequently to make sure these changes have not altered the behavior of the code. Ideally, you do not want to do a refactoring overhaul once your code is complete. This could be time-consuming and may cause more issues than you're fixing. You want to be making these refactoring changes when you're adding features. Refactoring the code at this point can make the addition easier to achieve, and saves you from needing a complete overhaul sometime down the line. So, what are these changes that you need to be making? Similar to the way we see patterns emerge in design, we also see patterns of bad code emerge. These are referred to as anti-patterns. Many of these anti-patterns are identified in the book Refactoring by Martin Fowler, where he refers to them as code smells. As a developer, this is a useful resource to have. Not only does the book describe these anti-patterns of bad code, but it also provides refactorings that you can complete in order to transform the code to improve the smell. The purpose of these code smells is to sniff out what is bad in the code. Similar to a drug-sniffing dog that you might see in an airport, you're going to learn how to sniff out these bad coding practices that are not supposed to be there. In the previous discussion, we asked you to discuss examples of bad code. I'm sure a lot of the examples that you pointed out we will cover in these lessons. Probably the most common example that comes up is in regards to comments. Normally, the issue is that code has no comments. This can be an issue for many obvious reasons. Having no comments makes it difficult for someone to understand what the code is doing, or should be doing. This could be another developer who's just joining the project, or a team member who might need to integrate some code. Or maybe it's even you, and you've forgotten how your code works. Having no comments is bad, but also having too many comments has issues of its own. They might get out of sync as the code changes. You might say that comments can be seen as deodorant for bad-smelling code. A lot of developers will try to cover up bad design by having a lot of comments that explain what the code does, or should do. Chances are, if you have a comment that describes a complicated design, you're covering up a bad design. You may also see reminder comments that say something along the lines of, "Don't forget to do this," or "If you make a change to this, make sure you update the code in this other method." These are also indicators of bad code. Using comments to explain a design could sometimes indicate that the programming language isn't appropriate. Perhaps the programming language does not support the design principles you're trying to apply, or maybe you're not using an appropriate programming language to support your designs. For example, in the early years of Java, the concept of generics did not exist yet. Developers previously would have to have comments to explain what they are doing with the code when casting types. Eventually, generics were built into Java, but until that time, many comments had to be used. This is a common occurrence in many young programming languages. Now that Java is a more mature language, you have no excuses. Now, don't get me wrong, I'm not advocating for no comments in the code. Comments are very useful for documenting the APIs, or application programmer interfaces, in your system, and also for documenting the rationale why a particular choice of data structure or algorithm was made. They also allow your code to be easily used by others. Like most things in programming, there's a balance you need to find, where you have effective comments in your code. The next code smell that we're going to talk about is duplicated code. You may have seen this in your own code, especially before you learned about object-oriented programming or design patterns. Duplicated code is when you have blocks of code that are similar but have slight differences. These blocks of code appear in multiple places in your software. Let's say you're working on a social networking website. A user can create textual posts that appear on their newsfeed, on a friend's wall, or in a group. You first create the ability to post on the newsfeed. These posts were visible by all the user's friends on their news feeds. Once that feature is complete, you then develop the code for posting on a friend's wall. Since you already have the functionality written for posting, you just copy and paste that code to reuse it for posting on a friend's wall. When you create the functionality to post in a group, you do the same thing. You just copy and paste that code for posting in a group. Now, as the website expands, you also want the ability to post pictures, and not just text. To add this functionality, you now have to update the code in all 3 places. What if you had other places in the code where a user could post? What if you missed one of those when you had to update the code to allow the posting of pictures? As you can see, if you would just combine the ability to post in one accessible method, all forms of post could use it. And when it came time to make a change, you would have just needed to update it in one location. This doesn't just apply to adding functionalities. You may need to update the algorithm or fix a bug. Having to update it in only one location will make it easier to implement the change and reduce the chance that you're missing a block of code that needs to be updated or changed. We talked about it earlier, but the DRY principle applies here. Don't repeat yourself. Now let's talk about the code smell of long method. This one is relatively self-explanatory. You don't want to have long methods. Having a long method can sometimes indicate that there is more occurring in that method than should be, or it's more complex than it needs to be. But how long is too long? It really depends. There's no magic rule that says that a method with X amount of lines is too long. For example, methods that set up a user interface tend to be naturally long, despite being focused on one specific task. This obviously depends on the toolkit being used. Generally, though, such methods aren't that complicated for their length, so a long method here might be okay. The code smell also could depend on the programming language. Smalltalk methods tend to be short, say about 15 lines on average. Designs in that language tend to have highly cohesive classes and methods, but also highly coupled. Some developers suggest that having an entire method visible at once on the screen is a good guideline, say no more than 50 lines of code. But there have been studies that programmers can handle methods of a couple hundred lines before they start to introduce bugs. Another matter is whether lines of code is even a decent measure of code complexity when figuring if a method is too long. Similar to having large methods, having large classes is also an issue. These large classes are commonly referred to as God classes, blob classes, or black hole classes. They just keep getting bigger and bigger. They normally start off as a regular size class, but as more responsibilities are needed, these classes seem like the appropriate place to put the responsibilities. But as one of these classes gets more responsibilities, these responsibilities tend to attract more responsibilities, and for convenience, where else are you going to put them but in this class? As you can see, just like a black hole, the class keeps getting larger and keeps attracting more and more responsibilities. Eventually, you're going to need extensive comments to document where in the code of the class that certain functionalities exist. And again, comments can be an indicator of poor design, and this is no exception. To avoid this, you need to be explicit about the purpose of a class, and keep the class cohesive so it does one thing well. If a functionality is not specific to the class's responsibility, you may want to consider placing it somewhere else. Like I said, these large classes tend to grow exponentially, so it's better to catch on to this code smell early. Trying to break these up after the fact can be difficult and time-consuming. On the contrary, having too small of a class is also an issue. These are often data classes. Data classes are classes that contain only data and no real functionality. Generally, these classes would have getter and setter methods, but not much else. An example of a data class would be a 2D point class that simply contains x and y coordinates. Think about what the data contained in these data classes is being used for. Instead of just manipulating it with the getter and setter methods, is there something else they are used for that could be placed in this class? Consider looking at the other classes that are manipulating this data. Would some of their behaviors be better placed in one of the data classes? For example, with our 2D point class, you could have various transformation functions that move the point. If a class contains just data with getter and setter methods, it may not be a good abstraction or a necessary class. A related issue that we see is data clumps. Data clumps are groups of data appearing together in the instance variables of a class, or parameters to methods. Let's say we have a method that does something with integer variables x, y, and z. This method might look something like this. If we had many methods that perform various manipulations on such variables, it would make more sense to have an object as the parameter, instead of using these variables as parameters over and over again. In this example, we could use a 3D point object as the parameter, which contains the x, y, and z values. So the method would now look something like this. And we would have a point3D class. So now, instead of using the 3 data values as parameters, they are now stored inside an object, and that object can be used in their place as a parameter. You need to be careful here, though. You want to make sure that you're not just creating data classes like we talked about. You want these classes to do more than just store data. So you might decide that the original doSomething method, or a useful part of it, should belong in the point3D class. Like a lot of these code smells, fixing one code smell can sometimes lead to creating new smells elsewhere in the code. So if you're creating data classes in order to fix the data clump smell, you're also going to need to resolve the data classes smell by making sure the classes have effective methods, not just getters and setters. On a similar note, having long parameter lists is also a code smell. This is one code smell that needs some compromise. Having a method with a long parameter list can be difficult to use, which is bad. However, the common solution to reduce the amount of parameters is often to have global variables. These have issues of their own and generally should be avoided. Having a long parameter list can make the method difficult to use correctly. By having a long parameter list, you are increasing the chance of something going wrong. Generally, these methods require extensive comments to explain what each of the parameters does and what it should be. And as we've discussed before, comments are usually just deodorant for bad code smells. But what if they aren't commented well? Well, then you may need to look inside the implementation to see how they're used. This breaks encapsulation. So how do you win here? The best solution for long parameter lists is to introduce parameter objects. This is a common occurrence in graphics libraries. Sometimes there will be toolkits where they will pass in an object which gives the context for a graphics routine. So, instead of setting the details such as the pen color, line width, pen shape, opacity, etc. as individual parameters, you would just provide this context as a parameter object. So when the program needs to execute some drawing method, say draw circle, you don't need to pass in all the information about what the stroke should look like as individual parameter values. Now let's switch gears a little bit and talk about some code smells that occur when you're making changes to the code. The first of which is called divergent change. The divergent change code smells occur when you have to change a class in many different ways, for many different reasons. This closely relates to the large class, or God class smell. When you have a large class, it will have many different responsibilities. These responsibilities may need to be changed in a variety of ways, for a variety of purposes. So, poor separation of concerns is a common cause of divergent change. It would be nice if your class only had one specific purpose, as it should. This would reduce the number of reasons the code would need to be changed. and as a result, reduce the variety of changes that you would need to implement. If you find that you're changing a class in multiple ways, that may be a good indicator that the responsibilities of the class should be broken up into separate classes, and these responsibilities should be extracted into their own classes. The original large class would then delegate the responsibilities to these extracted classes. You've now resolved two code smells, large class and divergent change, with one design principle, separation of concerns. On the flip side, suppose you want to make one sort of change. You want to implement one small requirement, one sort of change. It would be nice if that change was in one place. You can't always do this, but it would be nice if it were localized. But say you wanted to make a change for a requirement, and it required you to touch a whole bunch of classes all over your design just to do that thing. Maybe that wasn't so great of a design. This code smell is called shotgun surgery, where, to make a change, you have to take a shotgun to your code and then deal with all the splatter effect. Violent, I know. We didn't name these smells, we're just presenting them to you. This is a commonly occurring smell. A change in one place requires you to fix many other areas in the code as a result. This could happen when you're trying to add a feature, adjust code, fix bugs, or change algorithms. Ideally, you want your changes to be localized, but that's not always possible. A change that only affects one or two classes is way better than a change that affects multiple classes. If you have to make changes all over your code, chances are you're going to miss a change or create issues elsewhere. Having modular code, though, is not always an option. There are sometimes changes that require shotgun surgery, no matter how well designed your code is. For example, say you need to update the copyright statement or licensing. You're going to have to change every file in your system to change a block of copyright text. You can normally resolve the shotgun surgery smell by moving methods around. If you find that a change requires you to make changes to many methods in many different classes, then that can be an indicator that these methods may be better consolidated into one or two classes. That's not to say, though, that you should move methods into one class so that you only have to make changes in one class. That's the large class code smell again. You should move them if it makes sense to. The fact that a change in one place leads to changes in other places does show that these methods are related in some way, so perhaps there's a better way to organize them. However, if it makes more sense to leave them as they are, then you may just have to deal with it the way it is. The next code smell we're going to talk about is feature envy. Feature envy occurs when you've got a method that is more interested in the details of a class other than the one that it's in. This sounds like a romantic movie. Long-lost lovers who end their relationship years ago are still in love with each other, despite being in new relationships. They're more concerned with the other's relationship than they are with their own. You, as the viewer, are just screaming at the scene that they should end their respective relationships and just be together. They're just never going to be happy until they're in the same place. Well, the solution is the same for this code smell. If it seems like two methods or classes are always talking to one another and should be together, chances are they probably should. If you have a method in a class that seems to like to talk a lot to another class to do its work, it may belong better within that other class. On a similar note, our next smell discusses the issue of when two classes depend too much on one another through two-way communication. This code smell is called inappropriate intimacy. Say you have two classes that talk really closely to each other, so a method in one class calls methods of the other, and vice versa. Should these classes be so closely coupled? Probably not. Likely there should be some way to remove this cycle. To remove the cycle, you can factor out methods that both classes use into another class. This might free up some of the close communication. At the very least, you should be able to make it so that the communication only occurs one way. Now, don't get me wrong, cycles aren't necessarily a bad thing. You may recognize that the state design pattern has cycles. There are going to be situations where these communication cycles are necessary. However, if there is a way to remove the cycle, that would be a good solution to make your design simpler and easier to understand. We previously talked about the law of Demeter, or the principle of least knowledge. That principle specifies which methods you're allowed to call. It's not just private methods you're not allowed to call. Even for public objects, there are specific rules as to when you are not allowed to call a method. The next code smell, message chains, potentially violates the law of Demeter. Say you have an object A, which has a method getB, and this returns a B object. On this B object, you call a method getC, which returns a C object. Finally, on that C object, you call upon it to do something. In this case, it could be that the law of Demeter forbids you from calling methods upon the B or C objects. Having these long message chains where you are calling, getting an object back, then calling again, getting another object is a sign that you may be violating the law of Demeter, and these are bad message chains. Bad message chains cause rigidity or complexity in your design. It also makes code harder to test independently. In order to find an object in the code, to get from A to C in this example, I have to navigate the chain and these objects' dependencies. You don't want to bake in a particular navigation to your objects. Let's say I want to rework my design and restructure those dependencies. If I do that, I'm going to break this code. That's a sign of a brittle design. That's not always to say that if you see a line of code with a chain of calls, it's a bad thing. Sometimes it can be fine. These message chains could be returning a limited set of objects that we are allowed to call methods on. If these objects follow the law of Demeter, then it can be a good thing. It's all circumstantial. Now let's talk about the smell primitive obsession. This is when you rely on the use of built-in types too much. These built-in types, or primitives, are things like ints, longs, floats, or strings. Now, obviously these are going to have to be used. However, they should only exist where possible at the lowest levels of your code. Overuse of the primitive types occur when you are not identifying abstractions and defining suitable classes. For example, you could conceivably just define or encode almost everything in your system as strings and put them in arrays. Your code ends up looking like something that was developed in the 60s. Back then, that's what you had to do. Since then, languages have evolved to allow us to define our own types for better abstraction, so you should be using that. Otherwise, you have a non-OO way of thinking. Here's an example for you. So here in Canada, we have postal codes. These may also be called post codes, air codes, pin codes, or zip codes, depending on where you live. Basically, it's a series of letters and numbers included in a postal address for the purpose of sorting mail. In Canada, our postal codes consist of 6 characters, alternating letter, number, letter, number, letter, number. So they look something like this: T6G, 2R3. You could easily store this as a string and deal with it as such throughout your system. However, that's what we want to avoid here. That's because a key abstraction would be buried in the detailed code, and not very evident when looking at the design of the system, say in a UML class diagram. There would be no clear separation between a postal code string and other strings in the system. Would parts of your system care whether the postal code was all uppercase or had spaces? If you define a postal code class, then you can store the characters properly there. It would be much more obvious that this was a key abstraction for the system. You could also include various methods to validate it or calculate the region. If you find that you are using primitive types often at a high level, then that is a good indicator you are not declaring suitable classes and having a primitive obsession code smell in your system. The next code smell that we're going to talk about is switch statements. Now you may be thinking, what's wrong with a switch statement? Why do they exist if they're bad design? Well, sometimes there's a need to have big, long if-else statements in your code. However, there are times that switch statements could be handled better. For example, if your conditionals are checking on type codes, or the types of something, then there is a better way of handling these switch statements. Here in this example, the say method checks on the type of animal, and has different cases in the switch statement to have the animal say something appropriate, like woof if a dog. You want to be able to reduce these conditionals down to a design that uses polymorphism. In this improved design, we can have dog and cat objects that know the appropriate thing to say when their say method is called. Have you ever written any code with the thought, we might need this someday? If you have, you violated our next code smell, speculative generality. Speculative generality occurs when you make a superclass, interface, or code that is not needed at the time, but you think you may use it someday. Maybe you want the ability to make subclasses or provide a different implementation eventually, but you don't actually need it right now. If you're doing this, you are introducing generality that may not actually help the code. You are over-engineering the code. With agile development, you want to be practicing just-in-time design. You want just enough design to take the requirements for a particular iteration to a working system. So, at the beginning of each iteration, you would choose the set of requirements that are going to get developed. That is all you need to design for. You can ignore all other requirements in your backlog because those may never actually be needed. As you know, software changes frequently. Your client could change their mind at any time and drop requirements from the backlog. Your design needs to say simple. You don't want to spend time writing code that may never actually get used. When you need to generalize, then you generalize. This change may take longer at the time compared to if you set it up beforehand. However, you'll probably save yourself time overall across the system by not writing code that you don't need. It also keeps your code lean, simple, and easier to adapt. Finally, we're at our last code smell, refused bequest. This occurs when a subclass inherits something and doesn't need it. Think of this like your great-aunt Trudy has sadly passed away. In her will, she left you with her prized figurine set. She has hundreds of these little porcelain figurines that she had collected throughout her life. As much as you loved your great Aunt Trudy, you do not have the need, the want, or the space for these figurines. What was intended to be a gift has turned into more of a burden. This happens in code too. Say a superclass declared some common behavior across all its subclasses. If you find that your subclasses are inheriting things that they don't use or need, then is it appropriate that they be subclasses of this superclass? Maybe it would make more sense for a standalone class. Or maybe these unwanted behaviors should not be defined in the superclass. If only some subclasses are able to use them, perhaps it would be better to simply define those behaviors in those subclasses only. So those are examples of code smells. They are really great indicators of bad code and bad design. I recommend that you review your code frequently for those code smells to make sure that your code remains reusable, flexible, and maintainable. If you're interested in reading more about these code smells, or want to know what you're supposed to do in order to resolve these code smells, you can check out Martin Fowler's book, Refactoring, Improving the Design of Existing Code. Just like you can't write a good novel with one draft, you can't write good code without reviewing and adjusting the code to follow design principles, apply design patterns, and avoid code smells. Refactoring is a very important, yet sometimes overlooked way of achieving good design. Now go deodorize your code.
Congratulations! You've completed all the video content for this course. Now next up are the remaining capstone assignments. You've already analyzed and critiqued a working software project for code smells. Now it's time to make the code more flexible and reusable by using design patterns. They'll be followed by an end-of-course quiz that will test your knowledge from all of the material that we covered in this course. See you next time.